say a few words about him. So.
Yeah, sorry. Forgot he was not here. Well, I probably should have. You have a. Good afternoon, everybody. Let's start this afternoon session with Tomasz Prosen from University of Ljubljana.
Okay, do you hear me? Yeah. Okay, so, yeah. Well, I would like to thank the organizer, Jose, in particular, for putting up this wonderful event. I would also like to say a few words about Chico, but probably I will wait until he comes, so maybe I can just continue this talk first. And but actually, the reason why I picked up this topic is because of my first encounter, probably the first and only encounter with Chico, where we discussed about this, and this was like 2016 in Cambridge, where this work, this kind of line of research was very fresh. We had one paper out, one preprint, not even a published paper, and I tried to understand how we can put this into the context of integrable systems. And as you see, even now we are quite confused. So this model is simpler. I mean, it's somehow in between, I would say, free systems and integrable systems, because you can say much more than about generic integrable system about this model. So I also found when I was overviewing my talk yesterday that autocorrect made a mistake, and it put, instead of rule 54, root 54. And then I found like a cute idea, so I left it. I just put a rule as a parenthesis. You see, rule comes from classification of cellular automata, for those who have some passion about cellular automata as myself. But root means now really probably some possible way of doing statistical mechanics. As you will see what I mean by that in my talk. So the idea is to have models for which you can essentially compute everything, and yet these models should be interesting enough to give us some physics. Okay, so so now this is my motivation. So I just mentioned a couple of things about our first encounter, but since we're not here, so I can still, just say that I found our discussion in Cambridge so inspiring that I decided to give this talk now, just to tell how much has this question developed since we discussed it. You mentioned to me that I should look at RSOS models around this model, and indeed I did. But still there are questions, and I tried to touch on my questions in the last slide, but most of the stuff we did is still kind of not, it's still somehow in the air. It's not really classified correctly, I would say, in terms of Young-Baxter and integrable systems. But anyway, so the idea is to have, I would try to connect it in particular for the students to the lectures of the school and to the lectures course by Hermann, where you learned about matrix ansatz, matrix product ansatz. And my motivation was, and is in this talk, is it possible to find time-dependent matrix product ansatz, which is an exact analytic description of dynamics? So we have a strongly correlated state, which is a time-dependent state, strongly correlated, well, finitely correlated state, if you want, where entanglement kind of in this state grows as a function of time. It grows modestly, it grows logarithmically, so roughly. I mean, it cannot grow linearly, it grows logarithmically in time, as you will see, but still it grows, and the state is described analytically at all times. So I think, to my knowledge, this is the first model for which you can do something like that. In particular, I mean, for the dynamics which is deterministic, so I should also stress that part. I mean, most of discussions in this school and workshop are about statistical mechanics, and statistical mechanics is usually about statistical systems. But I think statistical mechanics should also be about deterministic systems. At the end of the day, I mean, our models are deterministic. What we basically do, usually we basically just describe our ignorance by statistical description, but once we have a deterministic equations of motion, we should eventually really understand how they yield statistical description. So my models are really deterministic, as you will see. And yeah, as I already said, I will try to find minimal interacting deterministic 1 + 1D model about which we can know everything without any approximations or any assumptions for that particular equations of motion. And then I'll try to convince you that the model, in fact, has a generic physical properties. It is like a model of a 1 + 1D liquid. So it has ballistic sound and diffusive heat transport. Okay, so this slide I will probably go through very quickly. This is like just to present like state of the art of the literature, at least from the perspective of our group on this model. And if you're more interested about this, I invite you to look at our review paper, which we published last year, or no, 1.5 years ago, together with my former students. And in particular, there is this historic reference, which I found very inspiring. Actually, I was looking for this type of models like 10 years ago. And I encountered this CMP model by Alexander Bobenko and company, where they classify this type of deterministic Hamilton type, but ultra-local Hamilton type dynamics, reversible type dynamics. And out of this classification, the most interesting what appears is this rule 54. I'll explain it later. But then the first paper we did was this one with Carlos Mejia Monasteiro in J Physics. Then there was different ways. I mean, we have looked at different kind of statistical mechanics paradigm for this model. For example, like a steady state paradigm where you place a spin chain or cell automaton between reservoirs and try to study steady state transport. We want to describe, this is like a Markov chain then, right? It's a deterministic equations of motion, but you put the stochastic reservoirs at the end, so it becomes Markov chain. Markov chain, I will discuss this in detail, but I'll just try to go through the paradigms. And then with Berislav, we were looking also at the eigenspace, eigen problem for the Markov chain. So we try to find some sort of beta equation description. As you'll see, this is simpler than beta equations. It's not free theory. It looks like beta equations, but it's simpler. So I mean, here maybe I try to connect to talk of Fabian yesterday. I mean, he spoke of something like beta-like equations. We also call these beta-like equations, but they even, they are less, they're more trivial in a sense, but you'll see what I mean. Okay, and then there is this work which is, to my flavor, the most non-trivial part of this talk, which is about this matrix ansatz, which I'll try to cover a bit. And then probably this is something which I won't have time, but just to tell you that there exists also exact description of large deviations, a very large family of large deviations, full counting statistics for this model. Time states, so you can swap between space and time, and you can describe multi-time correlation functions as states in time. And you can describe them again as matrix ansatz, matrix MPS. So all these type of things. And then there was further developments which I was not involved into. So my former students and postdocs then kind of started work on this as well. Independently, for example, there is this very nice paper by Katja, Bruno, and Lorenzo, which was emphasized in PRL, and it got, I think, physics focus, this physics article and editorial suggestion. It was really nice work, where they describe exact thermalization in this type of dynamics. So before continue, I would also like to mention this guy. Sadly, he passed away last year. He was my student, Marko Medeniak, and I would like to dedicate this talk to him. He was involved in the central part of this research. In particular, result on time-dependent matrix ansatz was a fundamental chapter of his thesis. Okay, and he has this very nice paper, which I quote here, which again is picking up on this project, and they are using these results in order to provide exact bounds on entanglement dynamics in Rule 54. So you can treat Rule 54, which is a classical cell automaton, but you can treat it also as a quantum cell automaton. You look at off-diagonal elements of density matrix, and you can describe dynamics of entanglement, of operator entanglement of density matrices if you want, or operator spreading local quantum observables. And these guys, Marco, Vincenzo Alba, and Jérôme Daubaille, provide rigorous bounds on entanglement, which again I think is the first and only result of this type. Anyway, now let me go to the definition, and please feel free to interrupt me at any point, because at some points things might look a bit formal, so I don't want to get lost in formality. The talk should be about ideas. So I prefer to cover less, but if there is confusion, please stop me. So now this slide is just to define dynamics. So dynamics, as you see, probably I'm very passionate about this dynamics, even though it's so simple, but it's the simplest dynamics I know, which is interacting and deterministic. So, and it is a kind of paradigm of PDE, of integrable interacting PDE, for example, like Sine-Gordon on phi-4 theory. So it looks like it's a deterministic dynamics, but it has scattering. It has non-trivial scattering. So this is the rule. The rule is basically describing, there is a fundamental plaquette, and there are 4 cells, and these cells you can think of as south, east, west, and north, and south is a function of east, west, and north. So time goes vertically. In this talk, somehow time goes downwards, usually it goes upwards, but it doesn't matter. It's irreversible anyway. And so time is vertical, space is horizontal. So this ret is the new value of the cell, which is a function of these three guys. So it's like a leapfrog rule for solving, let's say, discrete the Lambertian of a wave equation, right? When you solve wave equations in 1 plus 1D on discrete computer, on a computer, this is what you usually do, right? You have this checkerboard structure. But now, you see, what I do now is slightly different than doing. So what I do now is this, this cell is the sum of these two minus this, or plus, doesn't matter because everything is mod 2, times the product of this times this. Yeah? So this gives my interaction. And if you code this in this standard coding of cell automata, this is like 8 possible function values of the output, and there are 8 possible bits, and this bit string is 54. So that's why equal 54. Okay, now this is what happens if you just run dynamics for a finite time. If from some random initial condition, then you get this kind of movers, left movers and right movers, which go with speed 1, and they scatter, and whenever they scatter, they experience a shift. So there's a simple shift, there is a single shift, so everything is Z2. So I mean, it's like what you know about, let's say, models like Sine-Gordon, but there everything is continuous, now everything is discrete, so there's a single shift, and a single species of solitons, namely simple speed, 2 species of solitons, left movers and right movers. Now, you might think, okay, this looks like boring, right? I mean, but it's not quite. I mean, there is some interaction, and this interaction makes things interesting. And you see this, the fact that you have this interaction makes things behave like a typical gas. I mean, or liquid, if you want. You can make things more interesting, and just to motivate you that there is kind of life beyond this model, which is of the same type, maybe more complicated, probably more complicated, but there is not much we can say about this model, but just to motivate you. I mean, what we are doing currently, or we are thinking currently to do, is one of these models is the two-species model. I mean, it's a two-species version of this model, where you have 2 flavors, like blue and red. And it's like fermions. It's like classical fermions. So when different colors meet, they go through. When same color meet, they experience some sort of Pauli exclusion, so they scatter. Right? It's classical fermions, if you want. This model actually seems to be integrable, but we don't know how to, again, well, not for this model, we don't know much. In this paper, which we published after 2 years of having this project somehow under discussion, but then we said finally with Katja, we should publish something, I mean, just before we forget. So we don't have much. We have construction of local charges, which is empirical, not really analytical, but we show that there is an extensive number of local charges, so linearly many for a chain of size L. And I can just convince you that there is interesting statistical mechanics of this model. So for example, these are typical different initial conditions, right? Low density, medium density, high density. At high density, sorry. No, what's happening? In high density, you see that there are some sort of, well, I don't know if there are bound states, but there are some sort of collective states which emerge, like these striped quasi-particles which kind of scatter collectively and so on. So it would be great probably to understand this much better, but this is just to motivate. Now let's go back to a simple rule 54. So what we are doing now is try to provide a Markov chain description of this model. So this is like what you do when you study classical mechanics. You can consider trajectories, right? You can consider motion of trajectories, but you can consider also motion of ensembles of trajectories, which you call a Liouvillean dynamics. So now what I'll do now is I'll consider Liouvillean dynamics for this model. So Liouvillean dynamics means now I have a probability vector for all possible configurations. There are 2 to the n of them. This little n is the size of the system. So now I have a matrix and a power of t to this matrix, which gives me dynamics after time t. And the way I construct this, I don't know why this doesn't work so well. So the way I construct it is this what I would like to think of as a quantum circuit protocol. It's like 3-qubit gates, right? So first there's two half layers. First half layer updates the even spins. So these were like 1, 2, 3, 4, 5. And I'm sorry for these colors are not the best, but you should see probably some Arabic numerals here. So 1, 2, 3, 4, and so on. So now this is the first half-time step, which updates the even guys. The red is the updated value. And then there is a second half step, which updates the odd guys. So now you get from this saw of initial data, you get this saw of the final data after one time step. But now I try to imagine that this is like a quantum circuit, if you want, or in this Faddeev type of notation where you put indices indicating spaces under which this acts non-trivially. This is like applying product of commuting gates. These gates commute when they share a single index. They would not commute if they share, so this qubit is just a control, right? And this control, if they share a control, they commute. If they would share 2 qubits, they wouldn't commute. So now this is an even layer and odd layer, so basically dynamics is split into the even layer part, odd layer part. The only thing which is non-trivial is what happens at the boundary. So at the boundary, you place a 2-layer gate, like here. For example, this guy doesn't have you treat dynamics on a finite system. Now I'll try to convince you how to make stochastic boundaries. So on the right, if there is no guy, you have to do something stochastically. So you imagine there is a chemical reservoir of solitons, of kinks, with some chemical potentials. And these chemical potentials you describe in terms of these probabilities, alpha, beta, gamma, delta. And so you have this right and left gate, which describe what happens to the rightmost guy on even side or leftmost guy on odd side, which is side number 1. Okay, after the end of the day, I mean, what you get is this Markov chain. And this is what happens if you run dynamics for this Markov chain. This is a kind of a stochastic trajectory. You start with some initial condition, you put some stochastic reservoirs on the left and on the right. Now these bits which are red and these bits which are blue now indicate the cells which are flipped on and off on the left and on the right. But the fact that there is more red than blue means that the red is hotter, which means that there is larger chemical potential of solitons on the right, which means that you should also imagine that there is a current of solitons from right to left, which you actually see, right? So one of the, let's say, goals of this game is to have the steady state which describes this probability vector and to have observables like currents and correlation functions and all that. This is one way of doing this. What is also nice about this dynamics is that you can prove Perron-Frobenius theorem. You can basically prove conditions in Perron-Frobenius theorem which guarantee ergodicity of this type of dynamics, namely existence of a unique steady state and exponential decay of correlations. This you can do with the idea which I like to phrase as holographic ergodicity, namely you can show that these stochastic boundaries are enough to connect any pair of states, any configuration to any other configuration via a path in the Markov graph. I will not go into detail, but I'm happy to discuss with anyone who's interested, but that's one of the few examples I know when one can really prove, conditions for Perron-Frobenius theorem for interacting system. Now, so how can we produce steady state? So now I'll give you some algebra, which works kind of magically, but it's not really understood why it works. So suppose you have a pair of matrices. So basically I construct a matrix product solution for you. Matrix product solution for the steady state. You should compare this, for example, to solutions like ASEP, TASEP, or so on in the literature, which are for a different type of dynamics, which are for stochastic dynamics. This is deterministic dynamics, but still solutions formally are looking similar. So you have 2 matrices, W, 0 and W1, where 0 and 1 refer to 2 physical states. So you have a vector of matrices. Now these matrices are finite dimensional. They are 3 by 3. Actually, you have 4 matrices. You have a pair of W0, W1, and then you have a pair of W0 prime, W1 prime, where the only change is that they change these parameters, which are called xi and omega. So xi and omega are something that you should compare to what people call spectral parameter, but now they are 2 parameters. They are 2 complex parameters, formal complex parameters, which you should somehow fix to get the solution working. Okay. So now there is some magic, and that magic means that there is this commutativity condition, triple commutativity or cubic algebraic relation between these matrices. So this P is just a permutation operator which implements dynamics. Basically, this can be written in Faddeev type notation or in components if you want. In components means simply you have to permute the components of the middle spin, right, according to the rule 54 dynamics. And then this is like shifting this, what we call a delimiter matrix, for 2 sides. So once you do this, it's the same as when you shift this guy for 2 sides. That's kind of nice, right? So it's kind of almost like a zero curvature condition, right? Okay, and yeah, so you see I forgot to stress, but this is a particular matrix now which also enters the game, which we call delimiter. And now you can make an ansatz for the steady state. Okay, and the ansatz requires these bulk relations plus these boundary conditions. So these boundary conditions have to create the delimiter, and then this delimiter travels left to right. they have to swallow it, and then there has to be another boundary equation which speeds it again to a different parity of sites, and then it travels from right to left, right? So that's basically the way you compute, you show that this is a steady state of this problem. So steady state of this problem has to be formally written like a left vector, a string of w prime, w prime. This prime interchanging w and prime is because of the staggering nature of the problem. There is the even and the odd sides which have to be treated differently. And then also there is a staggering in time. So see when you go to a next layer in time, the next half layer in time, you have to switch between w and w prime on the even sides, for example. Even sides are at least 4 sides, right? One has w, one has w prime. There's also a curious structure of the boundary vectors. The boundary vectors have to have some information about the boundary states. Boundary is a two-side boundary. So this is a 3-side evolution. I mean, the gate is 3-side gate, but the boundary is 2-side, right? There is some correlations also that boundary has. So that is also reflected with the fact that boundary vector has to depend on 2 physical indices, 2 quantum indices, if you want, at the side. Okay, I already said the main idea. So the main idea is now you have these equations and the bulk equations, and then you just shift the limiter back and forth, and you, at the end of the day, establish that u even times u odd on some vector, which is of this type, has to be equal to lambda inverse times p. So there is this formal parameter lambda which appears, which is the eigenvalue parameter, which in this case should be 1, right? But it's still, there is a formal parameter which we have to allow here. Later I will include this parameter arbitrary, not forcing it to be 1, when I will look for steady state, for Markov eigenvectors, for the spectrum of the Markov chain. This is for the steady state. For the steady state, eigenvalue is 1, but for the excitations, this will be different. Okay, now, very nice. So you see, now the question, of course, there should be some compatibility conditions which would fix at the end of the day the values of the spectral parameters, right? And indeed, if you try to solve these equations, you see that these left boundary equations result in compatibility condition between boundary parameters, alpha, beta, and the spectral parameters. Right conditions, left conditions result in this pair of equations. Right conditions result in the other pair of equations, connecting the other bus parameters to sine omega. Now, if you ask for mutual compatibility of this over-constrained system, then you get that spectral parameters have to be these particular expressions, which then gives us the complete solution for the steady state. So that's very simple, right? It's probably even simpler than for ASEP because the matrices are finite. Now, since it's so simple, we can ask a more ambitious question. Can we diagonalize the full many-body propagator with the similar ansatz? And remarkably, the answer is yes. Which, again, since we don't understand much about this problem, we also don't understand much about why this works. I can only show how it works. And of course, I'm very happy to get any ideas of why this works the way it works. So what we do now is we introduce inhomogeneity parameter, which we may call a momentum. It's a multiplicative momentum, so I call it Z. So now what I do is I will try to write a more general class of matrices which now depend on position x through these linear combinations of constant z to the x and z to the minus x. It's like plane wave. If you want, it's like a plane wave construction, right? So what we do now is we construct slightly larger, but not much larger, slightly larger auxiliary space, which is like a qubit times what was previously an auxiliary space. So it's 6 instead of 3. Before it was 3 by 3, now it's 6 by 6. And we get this, so there are 3 parameters now, sine omega and z, the momentum. So if you want, 2 eigenvalue parameters, 2 quasi-energy parameters, and 1 momentum parameter. And then there are 2 new matrices, F plus, F minus, which I don't spell out here for simplicity, but you can check it in the papers. So this is the ansatz, and somehow by asking consistency, which I will not even spell out in detail here, but again, it's rather straightforward, you can find explicit form of these matrices, and then again, asking consistency of this type, similar to this, we can write boundary equations and the ansatz, which has now spatial modulation. We get, at the end of the day, compatibility condition, which result in what we called modified, beta-like equations. So now, this is very simple. It should be considered really as much simpler than beta equations because now it's an algebraic system of 3 complex parameters. One is called momentum. The other 2 are called components parts of the eigenvalue. So that you split the eigenvalue in two parts, lambda left, lambda right, and together with the momentum z, they form this set of algebraic equations, and the roots of this give me exactly the eigenvalues of the Markov chain. So you see, I mean, even if you look at this spectrum, right, it's like a daisy. I mean, it's this nice daisy structure. So it's a kind of onion shell structure. It's like a shell model, if you want, of the spectrum. So it's something simple has to be, no? I mean, it should be simpler than typical integrable system. Indeed, it's slightly worse than non-interacting system. Of course, what you can see here also that there are lots of degeneracies. I mean, this is for a system of size 12, I think, which means that there has to be 4,000 eigenvalues, but you only see up of the order of 100 eigenvalues, which means that these eigenvalues here are exponentially degenerate. I mean, these guys in the first, what we call orbital, are non-degenerate, but then the guys inside becomes twice, 4 times, 6, 8 times, and so on. Degeneracy is a geometric progression. So it has to be some nice algebra, but we don't understand. So, yeah. Anyway, but it's easy to get excited about this. At least it was very easy to excite me for a couple of years, even though we didn't do much progress afterwards, after we just constructed the solution. But now, okay, so how much time do I have? 5 minutes. Okay, so that should be the main part of the talk, so then I'll close. So now let's try to analyze, let's now try to attack the time-dependent problem. So time-dependent problem would be looking at what, in statistical mechanics, I mean, people would call a C-star dynamical system, C-star algebraic dynamical system formulation of this model. And since it's a classical dynamics, this C-star algebra is a commutative algebra. So it's even simpler than what typically you have in quantum spin systems. So what we have to do now, we have to construct local bases of observables. So now we are treating dynamics on the space of observables for an infinite system. So we'll consider a local basis, which will be these two sets of observables, where x is the position, which is an infinite line now, infinite integer line. X is an integer. And these two observables are 0 and 1, which means that you only know that at place 0, at place x, my observable, my spin configuration is 0 or 1. And this gives me the indicator functions for these two values. These two indicator functions are kind of complete basis for local observables. And then you can expand it to a complete observable for the entire chain by simply multiplication. For example, you can take R local observable, which is like product of, which is like constraining on R's consecutive sides, the values of cells, which is like a product of, in this way you build up the basis. I mean, if you've never seen something like that, probably it doesn't mean much, but if you have, then this is kind of natural, I mean, how to build the quasi-local algebra of observables. Okay, now, since I don't have much time, I will just tell you now how we solve this problem for time-dependent observables, and what's the upshot idea for that. So we actually, and then of course one has to discuss states. When one considers C-star algebraic dynamics, one has to discuss states. Here we will consider the most simple states, the strongly clustering states with no correlations. So the only correlations now build up because observables are time-dependent. States will be infinite temperature. Let's say infinite temperature state, maximum entropy, all configurations equally probable, or in homogeneous state, which will be like left semi-infinite part will be infinite temperature, right semi-infinite part will be ferromagnet, like all cells empty. It's like expansion into vacuum, if you want, and see what happens. Now, right, so now, what we will do now, I'll probably have to skip, but let me just give 2 minutes on this slide. So what we do basically, and this was the main contribution of Marco and Katja in this work. So what we do now, we try to write a time-dependent version of local excitations. So this is an observable, which means at position x, I know that my cell is up, and I don't know anything about the other cells. So now we look at what happens after time t. And for this system, since the dynamics is local, it can only spread by finite amount in finite time, what I know is that this guy can expand this into exponentially many local operators, which spread on 2t plus 1 sides, with coefficients which are these numbers. And these coefficients, it so happens, it's quite remarkable, can only be 0 and 1. So it's like a Z2 kind of expansion of a local operator, and these coefficients which are 0 and 1, one has just to provide some indicator of how to decide whether a 0 and 1. Now, I don't want to scare you with the algebraic expressions, which are probably overly complicated, but just want to give you a flavor for the idea. So the idea is, so there are these boundary states and operators which explicitly depend on time, but the idea is that basically you have to perform some sort of counting. I mean, basically you have to encode in the MPS matrices, you have to encode the result of a counting problem of how many scatterings you experience before you get to the top of the pyramid. So it's what we like to think of as a real space-time inverse scattering transform. We don't do inverse scattering in momentum as usual, but we work it in real space-time. So basically the configuration for, I mean, the value of this coefficient C pertaining to a particular configuration, you see this coefficient C, this coefficient C was depending on the full configuration for time t, which goes from minus t to t. This is basically the values of the bottom of the pyramid, which are zeros and ones. This is 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 0, and so on. This has to be decided based on this picture, and this picture tells you that this configuration can result as an initial, the question is whether this configuration can stem from a soliton which goes left on the top of the pyramid. There is a simple algorithm, which is P algorithm, polynomial algorithm, which you can encode in terms of MPS, which decides on that question. And the result is 0 and 1. So that's the product of these matrices. Right? I mean, that's probably enough what I can say at the moment. But you see, I mean, the fact that this is 1 means that this product will be 1. If this is not possible, the result will be 0. And then the rest is just to put Katya and Marco to work for a few months and to come up with results for observables. So for example, the simplest and the most general result we have is the result for the structure, dynamical structure factor or 2-point function of density. So density correlation function can be written explicitly as a function of space and time in terms of the sum of binomial symbols. And if you look at cross-sections of correlations at different times, you see what you have is basically two Gaussian-type peaks which move ballistically and they spread diffusively. So the fact that they move ballistically is reflecting the physics of sound, but the fact that they spread diffusively is reflecting the physics of heat. So it's the simplest cartoon model of liquid that I know, which is exactly solvable. Okay, and another problem is the quench problem, which we can solve. The quench problem means you have a random initial condition, you put it together with a ferromagnet or vacuum and that let it go. What you get is now a kind of correlated shock wave, and which you can also describe analytically. Okay, now that this was enough for physics, now the other results are concerning large deviations, which I will completely skip because I want to keep 1 or 2 minutes for the discussion. Can I? Okay. But just to tell you that there is similar algebra tricks for the large deviations, and I would like to just spend 2 minutes on these conclusions and outlook, because as you see, even though it's been now like 7 years since we are thinking, or at least I'm thinking about this problem, in terms of mathematical physics, we have not done much progress. We computed stuff, but we don't understand what we have. Yeah. And there are, actually, I managed now to also kind of excite some other theoretical physicists like Balázs Pocsgai from Budapest to think now deeply about this problem. And he has recently come up with a paper where they explain possible link to integrability of Rule 54. But what they find is that this is not, this model is kind of strange. It's not a single integrable system. It's kind of a mutually compatible limit of several mutually non-commuting integrable flows, which is really strange. I mean, I have not seen anything like that. I am not sure if anyone of you has, but I deeply recommend to read this paper by Balázs and his postdoc. Then there is this paper I posted a couple of years, a year and a half ago, but then I didn't publish it because I still kind of think of how to improve it. But the idea in that paper actually is connected to the suggestion that Chico gave me in Cambridge 7 years ago, 7 years ago, yeah, exactly 7 years ago, in January 16, right? Yeah. So his suggestion was look at RSOS models and formulation of this problem as an integrable Young-Baxter for RSOS. And indeed, one can do that for a model which is actually slightly generalized version, and this is what I really like, you can generalize this model to include stochastic or unitary transitions, depending whether you like to do stochastic or unitary dynamics. From mathematical physics point of view, it doesn't matter. So there is a big kind of possible generalization of this model, which I believe still remains integrable, and for which one can construct formally some star triangle relations, but they don't give us much, unfortunately. And yeah, with that, well, this model has been also considered years ago as a test bed for, let's say, ideas of generalized hydrodynamics, which are more general ideas, but since you have an exactly solvable model, it's nice to compare these ideas. So with this, I would like to thank for your attention and conclude. Thanks.
Thank you. Questions, comments?
In this, you said that you tried something with this young Baxter, and but I didn't understand at what point you arrived.
I can write star triangle relation in the RSOS formulation for the propagator, which is rule 54, or its deformation, so it can have also non-trivial unitary or stochastic mixing of transitions. So there are more weights, let's say. I mean, this is like a crystal type weights, which is deterministic, but you can expand this to have some continuous weights. So, and then there is two other matrices which you need to have the star triangle, which I call like Lax matrices, right? And that looks beautiful at first sight. You can construct transfer matrix, you can compute conserved quantities, and then you find that there is some strange functional relation which trivializes the conserved quantities, because you can get only what you already know, but nothing more. So that this transfer matrix is a function of the propagator in time, propagator in space, which is translation operator, and the conserved quantity, which is this soliton current. And there is a single conserved quantity. I mean, once you do the deformation, there is a single conserved quantity. All other conserved quantities of rule 54 are out. They are not, they are destroyed. So there is a single conserved quantity which remains. I mean, local conserved quantities. When I say local, I mean local conserved quantity. Yeah. Of course, there are. But all the checks, all the empirical checks of integrability seems to suggest this model should be integrable upon deformation. But this, so I think it's related to the fact that the R matrix that you construct in this way is not regular. I mean, so
maybe there is another approach to integrability somehow.
Yeah, it should be.
We are too much sticked with young Baxter.
No, I understand. I mean,
this type of thing,
as you see, I mean, we have computed a lot about these models using some other structures which we don't understand. But young Baxter somehow seems to be very inconsistent. I mean, you get mutually inconsistent things that, or trivial things.
We know a lot of models, for example, that in principle, for example, you can construct do coordinate answers, but then if you try to see what is the R matrix, probably exists, but it's a nightmare to find it.
That's another thing that we have not tried. Yeah, you mean to construct the coordinate ansatz? Yeah. No, that's something that we have not tried, but that's an interesting idea. Yeah.
Yeah, very nice work, really. So I wonder, these space-time pictures of the evolution of the automata looks like it is like a surface. It is a surface.
Yeah.
Have you studied the Raffling transition or things like that, or what the properties of that surface?
We try to think about this. We have not done much. Yeah, it's an interesting question. Yeah. To look at it as it's interesting because you see, I mean, I like to think of this as a two-dimensional StatMech model, right? Because deterministic dynamics enforces a kind of area law on the entropy, right? Because entropy can only be produced at the boundaries. When you take stochastic initial data, this gets entropy. But in the bulk, entropy cannot get produced. It's deterministic dynamics. So I would like to think of this as the equilibrium statistical mechanics based on rigid entropy. But
okay, thanks.
So you're considering the 54 rule. Are there other promising rules that can?
Yeah, that's a good question. Thanks for asking. Yeah, because I didn't have time to mention. But there are other rules. There are 4 rules actually which are interesting, which have particle-typed interpretations. There is rule 150, which is the free rule, which is the same but without the interaction, which is just wave equation in Z2, free particles. But then there is the interesting one, which is 201. It's like, we also had a paper on this with Juan P. Garajan from Nottingham, and it's interesting for people who do glasses or kinetically constrained models, because it's like a FFA model. Or if you want, it's a Floquet PXP model for people who do quantum simulations, these Rydberg atoms. I mean, so this model is interesting, yeah, because it has these constraints, and but everything that we do for Rule 54, we can do for that model as well. We have not done everything yet, but we have indications that everything can be done. So, and physics is completely different. Physics is kinematically constrained. It's not. So it seems that, yeah, the mathematics of these models is somehow not completely restricted by physics or vice versa. I mean, you can have interesting physics, a different type of interesting physics in the same category of models.
All right, I have to move on. Thanks a lot. Next speaker is Mohammed Vajapur from Teroy.
Okay. So this goes ahead, this goes back, right? So, can I start? Okay. First of all, thanks, José, for organizing this conference or workshop, whatever you call it. What I'm going to talk today is actually the problem. Even for a high school student, I can just present it. And then I promise you that all of you will understand that what is the problem. And then I guess that 60% of the things that I'm going to talk, you can already understand by just knowing the simple statistical mechanics of the undergraduate. Then maybe you just need 30% of graduate statistical mechanics to understand the rest of the story. So before starting talking about what I'm going to talk, I mean, let me start by saying some stories about Chico. So it was 2011. I was a postdoc of Giuseppe Musardo, who is not here at this moment. So I was out of nowhere invited by Salor for 1 month to spend in a meeting. And then I met there John Cardi, who I knew since 2007. And then I was saying, like, I'm looking for a postdoc, so do you have some names? And I remember he gave me 4 or 5 maybe, and then I just remember 2 of them. One was Jan Affleck in Canada, and the other one was Chico Alcaraz. So that was the way that I ended up in 2012 coming here, spending in this town for some time, and then of course I changed it to another place. Well, what I'm going to talk is actually going to be related with what we started in 2012 with Shiku and wrote a few papers. And I ended up to have an obsession with this problem. And somehow, in the last 2 years, I made some progress in analytical calculation of these things that I'm going to talk about. So, as I said, this project really started in 2012 with Chico, and then some other people had some collaborations. But today, what I'm going to talk is going to be based on the work that I've done. Well, it's going to be hopefully out in a few months, hopefully. So I will just talk about some basic part of this work, and the rest it will be just some sort of announcement. Okay, so what is the problem? So consider a matrix, square matrix, and define a submatrix of these matrices, Aij, and then you can actually take the submatrices in a way that the rows and the columns are the same rows and the same columns. This is my notation, so these I's are the sets of the rows and columns. So since I'm going to take those that they are equal, I'm going to adopt this notation. And then you can take the determinant of these guys, and then calculate the power of alpha of these determinants, and sum over all the principal minors. So if you have a matrix of n by n, we have 2 power n principal minors. So you need to calculate all of them, then power alpha, and do the sum over all of them. So this sum is actually 2 power n, so it's exponential. Okay, so this is the problem, as I promised. With the high school student would understand this. Well, the problem is that this problem for alpha bigger than 1 is an NP-hard problem. Okay, though it's so easy to say what's the problem, it's so hard to calculate it. And this has been proven for some alphas that this is actually an NP-hard problem, but of course it doesn't mean that for some problems or matrices you cannot calculate it. Right? Well, I'll give you one example that we managed to do. I mean, some non-trivial example. Well, so this is the problem. Well, last May when I was trying to give some premiere talk about this, I was just watching this classic dark comedy, and then I came out with the title that I just gave you. I think it looks like these days is pretty relevant, this dark comedy, so I suggest for all of you to actually take a look at this. Okay, so let's go ahead. So the overview of this talk will be, I'll go with some motivations, and then why this problem is interesting and how it's going to be related with what we did with Chico almost 10 years ago. And then I will show a Grassmann integral representation of this guy, which is going to be one of the main results that I'm going to present for you. And then I will try to solve the problem using some sort of a mean field. And then I'll give you an example of transverse field Ising chain and how we can actually, for a particular example, calculate these things. And then finally, the conclusion. Okay, so consider the normalized ground state of a quantum chain, which is expressed in particular local basis. It can be also global, but here let's focus on the local one, where n is the system size, and these are the eigenvalues of some local operators. For example, you can think about like, you have a spin 1/2, and then you have ground state of this spin chain written in a sigma z basis or sigma x basis or this kind of stuff. And then you will have exponential number of probabilities, right? So you can take this exponential number of probabilities and then put them in this sum and calculate Renyi entropy. Okay, so this is what you can do. Of course, when alpha is equal to 1, this is going to be the Shannon entropy. So here also I have an exponential number of probabilities. Well, it's very common for people to confuse this with the von Neumann entropy. The von Neumann entropy is kind of special example of what I'm talking about here, okay? So when you do this kind of calculations, you realize that for local bases, the Renyi entropy is actually follows the volume law, and also the Shannon entropy. This is what happens normally. And then this was actually studied a long time ago by a group in Saclay, which was Jean-Marie Stéphane played some role on this, and Pasquier and other people. Anyway, so they kind of came to this conclusion with numerical calculations that the B alpha at the critical point is a universal quantity. But it has been so far, well, still is a mystery, what are these universal numbers? This was one of the motivations for us to look to the same quantities, but this time instead of the full system, to the subsystem case. So in the subsystem case, you have a full system, then you calculate the marginal probabilities for the subsystem, and then you take all the probabilities, and then you calculate again the same quantities, right? So you can do the same thing with also the subsystem. And why we should do something like that? Because interestingly, a subleading term appears, logarithmic subleading term appears here, which this guy is again universal, and it looks like when, well, also for the Shannon it's universal, so this guy looks like for alpha bigger than 1 is proportional to the central charge of the underlying conformal field theory. Well, for alpha equal 1, it is very close to the central charge, but it seems that it's deviates from the central charge. So this was actually what we studied a long time ago with Shiku in many spin chains. Well, actually, I'm not sure that there is any spin chain that Shiku doesn't know about it. So now, for example, I mean, you may say that, okay, what else one can do with this quantity? I will give you some examples of what you can do with this quantity. For example, let's start with the transfer field Ising chain, right? This is the transfer field Ising chain, simple. And we know that for large H, we have a paramagnetic phase, and for smaller than 1, we have a ferromagnetic phase. And at H equal 1, we have a critical system. Okay, so actually, if you take these Renyi entropies, for example, for alpha equal 1/2, actually, you can do this really analytically exactly for all the parameters of H, but this is kind of valid for different alphas. So what you will see, for example, in the sigma z basis, let's go back, in sigma z basis, is that for large H, the Renyi is going to be almost going to 0, or exponentially actually small, but then we have this kind of behavior, and when you do the derivative of this guy, you see actually the singularity. Okay, so this is a quantity that it can actually see the phase transition. One can do also similar things in the sigma x spaces, because people, they like the sigma x spaces because it's the order parameter. And then you can see that actually with just some simple Cramer's value duality kind of things, you can realize that the H and 1H, they are related to each other. And you can find that constant term that I told you is universal is actually is going to be, well, actually, sorry, here I'm talking about the H bigger than 1 and H smaller than 1. So for smaller than 1, it's a logarithm of 2. At critical point, it's 0.2544. This is for the Shannon one. And for larger than 1, it's 0. So this number is, of course, still is a mystery. I'm not going to tell you what it is because I don't know still. Anyway, so there are mysterious universal numbers are going on, which we actually don't know what they mean in the conformal field theory. Okay, so that one was when I was changing the H. I can now sit at the critical point and change alpha. If I do something like that, then numerically, you can see that what happens is that for alpha is smaller than 1, we get kind of 0, and for alpha bigger than 1, we get a log of 2, and at alpha equal 1, we get something which I just showed you is a mysterious number. So all of these results are numerical, and that time they were able to go up to size 4T, which is still, I think, almost more or less the limit that we can do with the classical computers. Okay. Okay. So in 2016, with Sona Najafi, we were able to show that the calculation of Renyi entropy in this problem is actually a SPPM problem, which I just told you. It's the sum of the powers of the principal minors. And in this talk, I will show finally that we are able actually to calculate this stuff analytically, at least in some cases. In some cases, I mean the integer alphas. Well, this problem is also appears in some other problems that I will not go into the details of these things. But there are other instances that the same kind of sum of powers of principal minors, they pops out here and there. Okay, so this is the main result. You can write a Berzin-Grassmann representation of this sum that I told you, like this. So this AN, let's say that we want to calculate the power n of the principal minors. So we are going to have this AN, which is a block diagonal matrix made of these A's, n of them. And then we make the n copies of the chi and chi bar, that they are Grassmann variables. And then you couple them with this coupling. And then if you just do the Grassmann integration over all of them, you will get the sum of principal minors for any matrix. Actually, this is valid for any matrix. Okay. So to just have a bit of intuition, so mn equal 1, you can simply see that this is going to be something like this, and this is nothing except determinant of I plus a. So calculating the power 1 is actually a polynomial one, and this is really the special case. But then if you have n equal 2, this is a kind of coupling that you can see. Okay, so you can do the same game for any n, and just you are going to have more and more copies of the things. So these forms are kind of suggestive to do different kind of calculations, analytical calculations. At this moment, I will show you some basic one that, as I promised you, even with the kind of undergraduate statistical mechanics knowledge, it's easy to follow it. But we have done this with also using the variational techniques and different kind of other bosonization of the same guys. And we got similar results, okay? So this form that I wrote to you is actually has so many symmetries. So we started studying the symmetries of this system, and at the beginning we thought that there are just few of them, but they realized that there are so many symmetries that it took for us for a few months to actually kind of classify all of them. So there is a UN symmetry which mixes different species. When I'm talking about species, I mean different copies of the chi and chi bars that we have. You can mix them up, and then this guy has a lot of interesting subgroups. UN1 symmetry. We have axial U1 symmetry, parity, sectorial parity symmetries, and for a symmetric group, we have you can permute all the copies and stuff. In some special cases, we have particle hole symmetry, chiral particle hole symmetry, if you have anti-symmetric or symmetric matrices, okay? So another symmetry which we have is actually you can change the A with AD, which D is any diagonal matrix which does have an inverse, okay? So this is also another symmetry that we have for this system. Okay, so the symmetries can be kind of schematically shown here. So here it's kind of for the general matrices, this is for symmetric matrices, and this is for anti-symmetric matrices. So the consequences of the symmetries is that, you know, for the two-point functions, they have bunch of properties. I mean, so of course we like to do this kind of classification of all the symmetries, because later when we want to do some sort of a mean field, we want to know that which ones are broken and which ones are there. Okay. So yeah, so this is the basic version of the mean field, which, as I said, has a variational also version, which is kind of better in some sense, because we can also check the stability of the solutions that we have. Okay, so but for simplicity, I will stick with this story here. So let's call these 2-point functions like this, and this. So this 1 and 1. So now I'm sticking to n equal 2. So I just have 2 copies of the chi and chi bars. So I can define 6 of these guys. If I have, of course, these R's are for the matrices, right? So if I have a periodic boundary conditions, then I can remove also the indices R, which I'm going to do, because I'm going to tell you about the results of the periodic Ising chain. Okay, so well, what is mean field? Mean field is just putting this guy with these guys, which is an approximation, right? And then and this is equivalent to ignoring the fluctuations which is defined by like. Okay, so as I said, I'm going to consider some sort of a periodic boundary condition. So I'm going to have this guy equal to delta 1. Well, actually, I'm here putting also one extra conditions of these 2 guys are going to be equal, which is going to be delta 1, and this guy is delta 2 and delta 3. This is just for simplicity of because I don't want to deal at the first try with 6 parameters. I prefer to deal with 3 parameters. Okay, so after a bit of calculations, the mn equal 2 is going to be something like this. Now, this is a simple determinant, and the deltas are just the consistency relations. Okay? So these are the consistency relations, and this is the mn equal 2 that I'm looking for, which is supposed to be an NP-hard problem. Okay, so here I'm just showing a schematic diagram of what happens to the symmetries if the deltas, they have different values. So I have the same kind of diagram for general matrices and also symmetric matrices, but here I'm just showing the anti-symmetric matrix, because in the case of the Ising one, it ends up to be the matrix ends up to be anti-symmetric, okay? And you can see here that when the delta 3 and delta 1 are not 0, but delta 2 is equal to 0, all of the symmetries that I've written here are broken except the axial U1, which I'm going to come back when I'm going to show you the results of the Ising chain, okay? So, so let's go ahead. So what are the results of that consistency relation? So you can start looking all this, the solutions of these guys for the Ising chain. So for the Ising chain, the matrix is kind of related to the correlation matrix. So you get the correlation matrix of the Ising chain, and then you calculate 1 plus the correlation matrix over 1 minus the correlation matrix, and that's the matrix that you need to calculate its powers of the principal minors, okay? So we see here that the deltas, they have complex solutions, and these complex solutions, when you increase the size, they go to h equal 1, which is the phase transition point. So at phase transition point above h equal 1, we have a trivial solutions of all the deltas are actually 0, and when h is smaller than 1, we start having non-zero deltas. And here we just have the delta 1 and delta 3, which are non-zero. Somehow you can also see here the exact numerical calculations that the fluctuations are actually, when you are below 1, it starts growing, which is a sign that you probably need to take care of your mean field. Okay, so is it good? Well, so here I'm showing you the first attempt results. Well, actually, we have better results than what I'm going to tell you here, but I don't have the graph because we just realized that we can do better than what I'm going to show you recently. So R2, right, this is what I was looking at. You can see that here, this black one is the exact numerical calculation for size 30, and the red one, which is this one, is my mean field result. And then you can also compare this one, which is size 20, with this guy here. Well, of course, we can see all these linear behaviors. We can actually show analytically that it should be linear. And then here, I'm showing you that the mean field results are actually showing some kind of a singular behavior at h equal 1. And then there was this constant that I was telling you. So the constant we can also calculate it, and that constant, as we were expecting for this problem here at h equal 1, is actually, we get the size 0. And this is the coefficients of the linear term for different h values, which is actually, though the size that we have is actually, I think, if I'm not mistaken, the size that we have is already 20, so it's not that big. Although it's not that big, the numerical result, the mean field analytical calculations has a pretty good compatibility up to h equal 1/2. Actually, as I said, we can even fix up also this part now with some games. Well, so it's kind of works. So let me give you some comments. So interestingly, the ferromagnetic regime, all the symmetries except the axial U1 symmetry is broken in this model, which we don't necessarily have a very good reason why this is important. I think if you understand the delta 2 from variational technique, it kind of gives some idea why it should be the case, but just by looking to the symmetry itself, it doesn't look like obvious, at least for me so far. And the negative, so if you do the same thing, for the negative magnetic field regime, then your results ends up to be bad, but somehow you can just with this simple duality transformation, you can actually fix also the h minus sign part too. Well, I didn't show that, so I'm not sure that this was a relevant things to say here. So 2-point functions also, when you look at these deltas close to the critical point, you can also find out all these hyperscaling kind of relations and some new exponents and stuff, but I didn't mention it here. So, and of course, maybe for some people surprising, maybe for some not, it's a one-dimensional Ising chain, so you don't expect mean field works, but somehow if you pick the right, well, I don't know what right means, some particular degrees of freedom, then it works. Okay, so this here, the degrees of freedom that I'm working with, the mean field is actually suitable for those kind of things. Well, the mean field that I'm talking about. So, so we kind of solved also the same problem for to just benchmark our analytical calculations for the discrete Laplacian matrix, which just really a simple matrix of some diagonal elements are 2 and the first of diagonal elements are -1. So probably may look a simple question, calculating the sums of powers of principal minors, but actually it's not a trivial. Even for such a simple tridiagonal matrix, it's not a simple calculation. Well, at least it wasn't for us, because it took a couple of months to figure out all the things. So, but in that case, we were able to calculate for all the alphas, and then we benchmark this, the mean field, and actually mean field also gives the good results for that. So it's not like the mean field is gonna work for a matrix which is a long range necessarily, right? Because somehow you need to change your point of view, because you may say that the Laplacian is just a short range tridiagonal matrix, but since you work with the principal minors, somehow different parts of the matrix, they start to have some sort of, well, let's call correlation with each other, so it's not necessarily totally a short range things. Anyway, as I said, we figured out some hyperscaling relations, mostly for the anti-symmetric matrices, which was pretty relevant for the Ising chain. Also, there are some other alternative ways of writing these things. As I mentioned, you can bosonize the relations that I showed you, and do some other kind of techniques, use other kind of techniques to get some estimations. Now, let me conclude. So it looks like the SPPM is useful in the calculation of Renyi entropy, and there are some DPP problems that people that they do this kind of machine learning in DPP, they use, they also looking for this kind of thing. This was the community that I learned from them, that this problem is actually an NP-hard problem. So we found a Berzin-Grassmann integral representation, which we used to do the mean field calculation, and finally calculate the Renyi entropy of the transverse field Ising chain. Okay, thanks a lot.
Thank you, Mohammed. Questions? If you go to higher dimension, do you think your mean field can improve?
You mean?
Because you apply for 1D and seems to be
well,
but if you go to
so the higher dimensions, you mean the Ising higher dimensions? Well, here it was I can exactly map the problem of one-dimensional transverse field Ising chain to the SPPM problem. But for example, the two-dimensional one it doesn't have a simple fermionic version. So you already need to actually do some extra kind of things to break the problem to
Maybe the question to reformulate is, can you identify?
But what I said, if you have higher dimensional fermions, free fermions, all these things that I told you, they are going to work. Also, the time-dependent ones are going to work. So this part, as far as you have the free fermions, everything works.
In an interacting system, can you define?
Well, so far, well, it took already 10 years to take care of the free fermions, so I don't know how many years it's going to take to take care of the interacting one. But at this moment, we are more focused on just taking care of this free part.
Sounds exciting.
Yeah.
For me, somehow, it's a surprise that you have a mean field system which normally neglects fluctuations, right? And you say that you have the result for a model that usually those fluctuations are very important. So
Use of?
those fluctuations are not overcome by mean field, you know. This does not mean, I don't know, maybe somehow you transform this problem of large fluctuations and whatever into something which is very simple. I mean, you are in the right modes of your problem. Is this right?
Yes. That's what I meant with kind of, you are in a particular kind of degrees of freedom that it actually those fluctuations.
You convolute it somehow that you end up in the correct modes.
Yeah.
But this is because probably of integrability, no?
Well, I don't know. I mean, I'm not sure, but I don't see where the integrability should play a big role here. But I can say that also I haven't done some calculations on something which is not integrable. So, but my intuition tells me that I don't think that integrability is important here. I think mostly the kind of degrees of freedom that I'm taking is kind of more suitable for the mean field. But this is more like an intuition.
Okay, any further questions? Well, if not, let's thanks Mohammed again. Next speaker is Germán Sierra from Madrid, Consejo Superior de Investigaciones Científicas.
No, not that. So this is this. Ah, here it is. Okay. Well, Chico disappear. Took expectation value. Okay. Well, shall I start? Jose, ahí está. No, Chico is not here. Ah, yeah. Okay, so let me start. So I want to thank Jose Hoyos and Jose Javier for the invitation to come to the school. Can you hear me well? Okay. So to come to the school at the workshop, and it's an honor for me to be here and to celebrate the 70th of Chico. Well, not yet, 70 is tomorrow, right? We are in the minus epsilon. Okay, so I will start by some memories of my relationship with Chico. They go back to the year 2005. I think I knew Chico before, but my memory really identified this spot. This is a workshop in China. We were together with many other people, actually. So before the workshop took place in Tianjin. It's a city, big city nearby Beijing. But before going to the workshop, we were invited to visit the Yellow Mountains, a beautiful place in San Luis del Rio, actually. We had to pick up a plane, go there, and then go back. The meeting was differential geometry and physics. And there was the occasion to opening the building of the Institute of Mathematics that was founded before by Cher. Okay. Unfortunately, Cher died a few months before, so Cher was not able to be there. And then you see, it was a few days, and it was in Tianjin, this city. Well, this is a list of the proceedings. There were proceedings. And then you can find many people there, people we know. And here is the contribution by Chico that he probably will remember. It was about tensor networks. A matrix product ansatz solution of unsatisfiable interactive vertex model. Okay, that was your contribution with Ferreira and Anderson, I think. It was Anderson Ferreira. Okay. There were many people like Murray Bachelor is there. Deguchi, von Gehlen. So there were really a lot of people in this meeting. And they took us here, they took a picture. This is the picture of just in front of the building. Well, actually the picture is pretty bad. I couldn't identify myself. But I could identify two persons. One was Ludwig Fadeev. Fadeev was the chairman of the meeting. and you can identify him just by the size. And then I also identify Murray Bachelor for the glasses, right? But Chico, I don't know where you were, you identify yourself. I don't identify myself. I certainly was there, but Vladimir, I think, was also here, right? So one has to apply some kind of decoding protocol to identify oneself. Okay. But you see, the beginning, the building was really amazing. And this is now the Institute of Mathematics. Okay, another souvenir was, for some reason, we were coming to China quite often. And then this is another place, Chongqing. 2013, here we are involved in a serious discussion. I don't remember what we were discussing. But we were not alone, we were with Murray Bachelor. I think Murray was the guy who took the picture. Right, it's on the top. And the other picture, you see also Vladimir, but this was another, I think, another occasion. Probably Wuhan, because we were in Wuhan with Xinwen. In Wuhan, right? Tianjin and Wuhan. The visiting Xinwen. I mean, this colleague that was talking this morning. So all these were the occasions to meet and then to prepare a visit for Chico to Madrid. And that was the beginning of our scientific collaboration. It started with a work with Vladimir. It was about computing share information in statistical mechanics, stationary states of a stochastic process. That was the first work we did. Chico and Vladimir were in Madrid for kind of sabbatical. You took a sabbatical, a few months in Madrid. Then after that, I came to San Carlos. Then we did a work with a student. We did a work on the cited entanglement in cited states in conformity theory. This was done here, San Carlos. And then much later, we did this work on equipartition of entanglement entropy that we started from some problem that we started discussing here, and we ended 3 years ago, something like that. But at that time, I was not here. I was in another place. Okay, so this is, well, we have 2 more papers, but they are related to this work. So these are the more significant. And I must say I enjoy a lot, Chico. I enjoy a lot working with you on these problems because we went far beyond what we expected at the beginning. Okay, so now let me go to the topic of this talk. Is the algebraic Bethe circuits. Okay, let me tell you what are my collaborators in this work. There are 3 students. Alejandro Sopena is a PhD student in Madrid. Then Mas Undergordon, he's also a student, but has been most of the time in Los Alamos. But now he's going to Madrid for a while. And Diego García Martín has been also a PhD student. He already finished, and now is in Los Alamos. And then Esperanza López, who is a senior colleague in Madrid. Okay, this work is published already. Here is the archive reference, and this is the journal, Quantum. So the problem is, in a few words, the problem is the following. We know that in many integrable systems, there is the Bethe answer, algebraic Bethe answer. So there is a way to construct the eigenstates of the Hamiltonian. Okay. Then, but this is an analytic method. In general, in practice, it's very difficult to compute the eigenstates. So you have to solve the Bethe answer equations, and then you have the wave function. And now you would like to see if you can actually implement this protocol into a quantum computer. Okay? So you want to use the Bethe answer to construct wave functions giving a quantum computer. Okay? That's the problem. So, but there are 2 ways to present the Bethe answer. One is the original one by Bethe this year that applied to Heisenberg. It's a superposition of plane waves. The momenta of the plane waves satisfy the nonlinear equations, which are the Bethe answer equations. Okay? That's the case of Heisenberg. Isotropic. There is also the anisotropic case. This is called the XZ Hamiltonian, and the same story. Now the beta equations change in terms of the anisotropy. Where delta is 0, we are left with the XY model, and this can be solved simply by a Jordan-Vivier transformation. So in this case, it's very simple. You don't have to solve any equation at all. Okay. That was the coordinate beta answer. But there is also a version, the algebraic beta answer, where you introduce R matrix that satisfies the Jan-Buster equations, and then you construct the eigenstates of the Hamiltonian like this. It's a product of B operators acting on the vacuum, which is all the zeros, and this operator B is this entry. This is an entry of the monodromy matrix. Okay, so it's an entry. You have to multiply all these matrices R. You put a 1 here, a 0 there. This is the incoming state and then the outgoing state. So this is an operator mapping n space into n space. Okay. So this is the way you construct and the lambdas are the rapidities that satisfy the corresponding beta-ansatz equation. In this case, we are considering the 6-vertex model. So their matrix is 4 by 4, and then it's characterized by these parameters. So lambda is the rapidity, delta is the anisotropy. Okay. In particular, if we consider simply one magnetic state, we multiply all these R matrices in a row, and the R matrices have only one parameter. Okay. That's very well known. So the question is, if we can use the beta-ansatz to construct interesting quantum many-body states using a quantum computer. Okay, that's the problem. So this means the following. You will have a number of qubits that will correspond to the number of sites in the spin chain. Then you have some initial state. 0 means the reference state, the spin up, or the 0, quantum state. Then there will be some unitary transformation, and finally, you will get the beta state. That's as simple as that. So the question is, can we construct a matrix U from the beta-ansatz? Okay, as simple as that. Suppose you do that, then we will put a label in the machine, beta inside. So this is a joke, okay? So but it means that theoretically we will have a quantum machine based on the beta-ansatz. So applications were prepared non-trivial state for other algorithms, like quenching, like time evolution, compute expectation value of observables that are complicated, and also you can benchmark quantum computer machines that are now being built. Okay. Okay. So this program has been carried out, or is at the beginning of the development. There are first papers by Nepomniachtchi, that you know, Rafael Nepomniachtchi, and a group in Virginia. What they were doing, they were using the coordinate beta-ansatz to construct a quantum circuit that realized the beta states. Okay, so the first version. And the circuit is basically this. Well, this is a very sketchy. Here there is a number of incoming qubits in the initial state. Here you prepare a decay state, so a superposition of all the states with one. Then they introduce auxiliary qubits in order to add these phases here. And this is not kind of obvious to do. Okay, but they managed to do so. Here you have the superposition of all possible states, but then here implements these amplitudes. Then finally they reverse this operation, but they are still left with some ancillary qubits, and as many as m qubits. The m is the number of magnons that you have. So the beta state appears in this line, but it's a bunch of qubits, okay, appears here, but then to get this state you have to measure here. So there is a pixelation. So the probability of getting beta state, it goes essentially like the inverse of the factorial of the number of beta states. That's very bad. If m is large, the probability of getting beta state is very small. Chico.
Beta state, you are saying the special one that
Any.
How you select the eigenstate?
I will let you know. Here, in this case, just put in the momenta. So the rule is you choose the momenta to satisfy.
Okay, you choose the roots. You have to solve the roots and then just to produce the
Exactly. Perfect. Yes. So this way, this is a possible way, but has this problem. There is postulation, and the probability is very small if m is large. Okay. Now there is another observation that beta states are really tensor networks. Well, this was done already by Chico back in 2003, then some other people, and also, well, Kurepik and Bestraite, more recently. Well, here is, let me tell you a bit what Chico did, which was essentially what was presented in Tianjin. Okay? So this is a very nice thing. So this is the eigenstates, or the beta states can be written like this. So you see, these are matrices, E, and so. It depends on the, this is the where you have the magnum, okay, the spin down. And these four, you have to select these matrices, satisfying center conditions, are here. But this is really the putting the algebraic, the coordinate beta answer in a matrix product form. This is what it is, okay? So maybe one can improve the method by Nepomniachtchi and company using this version, okay? But what we will be using is the different setup that is due to Kurepik and Bestraite, well, Murk. This is the paper, the algebraic beta answer and tensor networks. So what they did was, okay, let me take algebraic beta answer and interpret it. And this is this expression I wrote of the vacuum. Here's the vacuum acting on the B operators. The B operators are these lines. One side is 1, and the other is 0. This is the opposite notation that we are using. And then finally, the final state is here at the top. But this is a tensor network. This is an MPS actually. And let me show you why. If you multiply all the matrices along a row, no, a column, you see, this is an operator that finally produces the spin. But here you got a bunch of indices that are contracted. Well, this is nothing but an MPS. This is what it is. The interesting thing is that the bond dimension goes like 2 to the m. So the more, the higher the number of magnums, the higher the bond dimension. But indeed, it should be like that, because this way you will be able to produce any eigenstate. And for that, not just the low line, but any state. And this is why you need 2 to the m. Okay, so that's nice. And then we will do now the following. So we assume algebraic beta answer, and then we want to get a quantum circuit. Let me think. Well, the first step is simply, it's very trivial, is to rotate this index over here and that index over there. So the R matrix will read like this. This is trivial, we haven't done anything. And now the tensor network that we have now with under this rotation will become this. So all these ones that are here appear down there, and the zeros here appears up there. And then you have now this structure, like all the R1s that are in a row, now they are in a diagonal, so on and so forth. Now, the number of degrees of freedom here is n plus m, which is the number of magnums, and at the end is the same. This is simply a rewriting of the beta answer. All right. Now, what is the problems? What are the problems of this? Well, there are two problems. One is that these are matrices. They are 4x4 matrices, but they are not unitary. For the rapidities that are solutions for the beta answer equations. So you cannot claim that this is a quantum circuit, because R are not unitary. That's one problem. The second is that there are a bunch of zeros here. that if you were to construct a circuit like this, supposing that the R matrices are unitary, at the end, to get the beta state, you have to measure here and get 0, 0, 0. This is the population. But as in the previous case, the probability will go to 0, exponentially. So you got two problems at once, non-unitarity and the population. Okay? Now, the nice thing is that you can solve both problems at once, using something called the QR decomposition, iteratively. So QR is that you have a matrix, and then it can be treated as an isometry and an upper triangular matrix. Okay? This is what used to play the role of the singular value decomposition. But here we don't do that. We use QR decomposition. And let me tell you how this goes. So first you collect the R matrices in the other diagonal, which are different, and now you call it the new R. So the whole tensor can be written like this, a bunch of RT, TTTT, up to the M. That's the first step. Next, the idea is to kill these zeros at the end. So you simply absorb the zeros into the R matrix, and then you define a new tensor, G0. So you have already eaten a bunch of zeros at the end. Okay, now you have this G0 that will be multiplying one of these RT matrices behind. Okay, here is where you apply the QR decomposition. So this becomes a unitary matrix times a tensor G1. Okay, so you have reversed the step. Now you keep going. So now there will be this G1 that will multiply another another R, and again, you apply, again you get another unitary. So you keep going, and at the end you get a product of matrices which are all unitary. And then you keep going. And then at the end you get some G matrix that multiplying RT, acting all these guys, it simply is, again, a unitary matrix, and that's it. This is you get some number, but you don't care about the number, because you just normalize the state. So the final result is this. You have a product of unitary matrices whose size grows up to depending on the number of magnons, and at a certain point stabilize, and you keep going. Now, how many qubits you need? You have M, and then M minus M, and then the same number here. So you have to solve the problem, both problems. Unitarity, now you have unitary matrices, and you don't have to do oscillation. So this is a deterministic algorithm, okay? Here, okay. Well, this is a sample for one magnon. One magnon, well, this is the protocol we have been explaining, then at the end, so you start from here, and then this is the final state, okay? And these are the matrices for the one magnon circuit. Well, the G matrices have this simple structure, the unitary has this form. You see, the unitary depends on the momenta, P, depends on the momenta and on the level, on the step. So it's not the same unitary here, no. It varies. With this circuit, for 4 sides, you get this. So this is a magnon with momenta P, okay? Simple as that. Well, with more magnons, it's getting more and more complicated. This is the unitary matrices for 2 magnons. So it has a dimension 8. Okay, and so on and so forth. Well, now, up to now we have analytical formulas for this. Kind of tricky, but we are trying to understand the analytic. What is the analytic structure behind these matrices? Okay, so let me now discuss the case for the XX model. This is the one you solve by Jordan-Wigner. But here we don't do Jordan-Wigner. We are always with the spin operator. So here, what is the problem now? We have these unitary matrices whose size grows as we go down. But certainly you don't want to play with these guys because this is very difficult to implement in a quantum computer. In a quantum computer, you just play with 1 qubit gates and 2 qubit gates. So the problem is to factorize, to decompose this unitary in terms of more elementary gates. Actually, 1 qubit and 2 qubit gates. This is what you want to do. And in fact, this case, which is the free model, you can do in terms of these matrices. They're called F-syn gates. So you see, this is ion 1 here, and then a unitary matrix there. Okay. In the past, there have been protocols to do this kind of computation, but they are not the same. I mean, they are similar, but so there's in this case we can actually count the number of gates for the system, and it's quadratic. It's the product of number of size and the number of magnons at the times this. So it's quadratic. It's a quadratic dependence. So it's efficient. This protocol is efficient. The more interesting is the case of with interaction, so the X set. Well, here the unitaries can be prepared with these F gates, but the F gates are modified. The modification has to do with the element in the element at the diagonal element at the last entry. In the previous matrices are called in quantum information match gates. And the match gates are unitary matrices that satisfy the Leaf-Wu condition in statistical mechanics. Indeed, because Wu-Li is the one that tells you that you are working with a free fermion system. So these are the gates we were using before. But when we can here, we're using gates which are not like that. They're not match gates. So this is one thing. The other is that in this case, we are able to factorize in terms of these 2 cubic gates, but the number of gates increases depending on the number of magnons. And then if we count how many gates we need, it seems that the increase is exponential, which is bad. So it's bad, unless we find out a solution for this problem. So with interaction, it's like when you say, let me do the Jordan-Bigne, you go to a fermion with interaction, and then you do bosonization, but then everything becomes an approximation. Well, here we are seeing the phenomena, but in terms of these circuits. Okay. Okay. Now we also took a look what is the unitary form of Jan-Baxter equation. Okay, so we transpose the Jan-Baxter equation into an equation like this, which is, these are these P gates, which are unitary. These are rapidities, and then you want to flip, you need another matrices, which are also unitary. So this is kind of the unitary version of Jan-Baxter. And then, well, of course, we verify this wave function first numerically. So, for instance, we took a check of 24 size, then we verify expectation values, okay? So, with 2 magnons, this is the sigma C expectation value, this is the sigma X. We also consider 4-point expectation values in several situations with anisotropy delta 1 or 0.5 with 3 magnons, 12 magnons. So we deal up to 12 magnons. Okay, so solving a recursion, but purely numerical. Okay, so this is a check. This is a check of something we can do with the wave function, with Bethe, or with the circuit. So we made these 2 comparisons. And then we also put this stage in a quantum computer. So here the IBM quantum computers with 6, 7, and 8 size. These are the case of a plane wave with 1 momenta, pi, or some different momenta. And here you see there are several plots. So we are computing the expectation values, the comparison between exact, several protocols. So raw is what you immediately get from the quantum computer. But they are kind of mitigation techniques to extract the result. Okay? So these are the zero-noise extrapolation and some other methods. So, well, the results, you see, are pretty good, actually, if you perform these error mitigation methods. Then, this is another check. This is now with 2 magnons, with 4 sites on IBM Montreal, and 5, this other quantum computer. Well, again, the results are good. Here we have 0, well, this is XY, but this is with interaction, and then another state, but excited states, and these are ground states. So we really try to see how these things work in the real quantum computer. And then we also checked a master on quantum hardware. So here we took two magnums, and here the point was to make an initial state, and then so we have initial state. We go one way or the other way, so the final state should be the same. And then what we do, we make up the fidelity between what we are expecting, the theoretical result and the experimental, and then it should be the same. Okay. In both cases. And the fidelity is pretty good, okay? It's 95, 96%, okay? Well, so let me conclude. So first, this is the idea of using static summable models. You may study somehow applications to quantum computers, quantum information, and try to understand how this is processed. Then, of course, other things to do is to consider higher spin. That was to be interesting because this is the distributed answer. So we will see how implement here distributed answer. Hubbard, TJ, etc. Another curious thing, you compare this with, for instance, factorized scattering symmetric theories. When you consider, I don't know, Saint Gordon, and you consider the interaction, the scattering, you factorize total scattering in terms of 2x2 scatterings. So this is what you say is factorized. Well, here you are expecting something like that you will just need to give it a case, and not that many, just for integrability. So at this level, we don't really see how integrability improves the computation. You see? Maybe there is a way to find out, but so far, unless the free case, in the other case, it seems that you need exponential number of gates. Okay, but then what is the point of having integrability? You see this? Okay, and that's the last problem I mentioned. Okay, Chico, happy birthday.
Thank you, German.
Yeah, I think there has to be a way to.
Sorry?
I think there has to be a way to make this, to surpass this problem of exponential growth of the number of gates.
You mean a smaller number?
Smaller number, yes.
Yeah.
Because I remember, we had some results some years ago, numerical results, but I think there are other people who confirmed that, this operator entanglement for integrable systems grows logarithmically, so slower than for generic systems.
Okay.
And that has to manifest in this. This complexity. The operator.
All right, but the
operator spreading is much slower for this.
I see, but the probably was. But the point here is that you are not just focusing on the ground state, but any state.
Sure.
So maybe that's the difficulty.
Yeah, but
right?
maybe you should not. Yeah. Okay.
That can be the.
Maybe that could be the issue.
Okay. Yeah, because this thing works for any state actually. You solve the equations, make the equations, you plug,
maybe
and
you
then
don't ever want to compute these states. Maybe you don't want to compute these states. You want to compute local observers.
Exactly.
German, somehow, actually, is a beta state, so you have already given this information that everything will be given in terms of just these degrees of freedom. So in this sense, it's very special.
Yes.
Because if it would be non-integrable, you cannot write something which is the size of your system. That's maybe the origin of this log behavior. Instead of exponential one, you take a log, because actually you only need the roots, and you give the roots.
Yes.
So there is some already information in this problem that you bring up, and this may be. But if you understand correctly, this might be useful as somehow a method, not simple way that you can get the answer, and then you can compute the performance. For example, you sell this circuit, and so this you can check this computer, check another one, whatever. But my question is, who do these things? Of course, if you pick up, just give the zeros of the ground state, then you may at the end, you end up with this ground state. Okay, the wave function. So It's an application. But is there an application in general that you would say like scattering, calculate scattering of the wave functions or some even correlation functions you get then in the quantum computer? You believe that this is possible to develop more involved circuits that after get that you get?
Yeah, I think so. Yeah, for instance, well, in general, in the better answer, formally you construct the wave function, but you don't have it, really. So here you have it. I mean, physically. There you will be able to compute any correlator.
Just add more things in the circuit and go on.
Exactly. Of course, there will be errors.
Yeah.
That's the problem at the moment. Another thing you can do is to put, to make construct inhomogeneous models. So put vertical direction, vertical rapidities differently. And they will become a random system that you may explain, and then random rapidities on the side. So that's one thing you may look also. What the property of the many-body wave function, where there is a many-body localization, but these kind of things. Once you have the machine, you could do it.
So, hi, thank you. I have two questions. First, do you think it's going to be hard to write string solutions? The string, when you have, for example, the roots of the unit as your quasi-momenta, and then you're going to have problems in writing the operators, the unitary operators, to do that?
You mean to find the solutions of beta?
No.
No.
No, you have,
No.
you have the rapidities,
You have
right?
the rapidities.
But then you have to construct the operators, right?
Yes.
And usually when you have this, for example, the I/2 and minus I/2 rapidities, they are very tricky to build in a normal computer, right? So, because they give you a zero.
But here we are not assuming that the rapidities are real or complex. We are not assuming that.
No, you're entering the rapidities, right?
Yes, but it can be real or complex.
Yes, but I'm saying sometimes when you try to calculate in a normal computer, right, the rapidities in a finite system, when you have I/2 or minus I/2, for example, then the matrix turns out to be a zero because you have a zero times an infinite, and then you get a finite. And so it's the finite systems may be hard to do. That's what I'm saying.
But look, here we already considered that case. Here it is. You see? Here the rapidity. These are complex rapidities.
Yes,
Real
but
and complex.
not the units of the square roots of the unit I/2 and minus I/2. These are the two ones that I'm worried about.
But these are the ones. These are the two
Yeah,
rules.
but
I think our organization. I mean, these are the numerical solutions of the beta equations. And
and you do have these solutions. For example, probably it's for the isotropic model, so delta equals 1. But we can talk later. But it's just I tried to do it once in a normal computer, and I had problems writing the matrices for these particular solutions.
Okay, but here, let's see. Here we are using the unitaries, which are a cooking of the R matrices, and so far no problem. Okay. So far no problem, because they're not directly the R matrices.
The other question, is maybe it's I'm not sure it's a question. It's just an idea. Is that it may be very hard to start from a trivial state and write a quantum circuit to create a non-trivial state. And this is actually an open question, right? If you can get no trivial objects without having an exponential number of gates.
Exactly.
But if you try to rewrite your ansatz to start with some non-trivial entangled state, so as an input, you may need a polynomial number of gates to get there.
Indeed. Yeah, indeed. Yeah, here the initial state just zeros.
That's right. And so to start there and end up in the non-trivial state may be very hard. But if you start with some state which already has some structure in it and rewrite your scattering matrices to get to the state that you want, you may be...
This is a way what the people with the coordinate beta answer do. They start with the decay state, and there you have already entanglement. And then they put the phases. The problem are the ancilas that you have to kill. This problem we don't have it.
Okay.
It's a compromise.
Right, thank you.
Okay.
All right, don't see any further questions. Let's thank German again. We now go for the coffee break and resume at 4:30. The coffee break and the birthday cake as well. So let's get downstairs to blow the candle for Chico. Hello, everyone. Let's start the afternoon session, the second, the last. Is this the last section? Yes. Of the workshop, and we start with Hans Hermann from the Federal University of Ceará and other universities in Paris. Hans.
Okay, ladies and gentlemen, it's my pleasure to be here. First of all, I would like to thank the organizers for giving me the chance to be here and to present this work and to commemorate Chico's birthday. Okay, I have already put Chico's birthday here. So I'm very happy to see Chico in such a good shape, full of energy and full of creativity as usual and full of his generosity and ideas. And of course, I wish many more years of this creativity and strength, etc. I would like to remember that 35 years ago, you were 35 years old. We did this piece of work at which is completely Brazilian. Both of us were at that time in Brazil. Well, I'm not really in the field of standard field of quantum. My h bar is equal to 0 always, and I'm also not so exact as usual people here in this room. So my subject is much more mechanical. So I will talk about bearings. Bearings, I will explain what it is, and I will explain especially the difference between 2D and 3D, which is very striking. And especially I will tell you about the many degrees of freedom that you encounter in 3 dimensions. And then I will say something about how to frustrate these bearings, something about synchronization, and finally, if I have time, I will talk about space filling. Let me first present my collaborators. So these 2 persons here, Dominic and Rilder, are PhD students. Dominic from ETH and Rilder from Fortaleza. And the other ones here are professors. Suarez, who sends you best regards from Fortaleza. André, also professor in Fortaleza. And Nuno, who is now in Lisbon, professor. So bearings are structures in which spheres or disks move on each other without slip. So that are systems which the particles, or the disks or the spheres, are not moving translational, but only rotations. I'm not going, in my talk, there will be no translations whatsoever. Everything is only rotations, or if you want in a quantum mechanical language, spin. So this is my spin. And these bearings are, of course, of many uses. You know them here. You see some examples. And there exists also a continuum version of a solid which consists only of these rotating objects, which are not moving but only rotating. And this is the so-called Causera theory, which is a generalization of elasticity theory, which I will not talk about. I will be staying in the completely discretized system. I will not talk about the continuum limit, but I would like to mention this because this is certainly an interesting direction also to go. So, the way where you find these bearings that I discuss, and in fact, the motivation why I started to study this, are so-called shear bands. So if you take a system of disks and you apply what is called a triaxial pressure, that means you apply some kind of deformation from top, then the system side starts to slide on certain lines. It slides away. And in this sliding region, you observe rotations. You see, here you have, I make a zoom here more. You see, this is like how it looks in these shear bands. The gray particles, they do not rotate. The white ones, they rotate clockwise, and the black ones rotate counterclockwise. And what you see is that in these shear bands, spontaneously you create situations in which you have black ones touching white ones. It means the two are actually having no slip at the contact point, which reduces considerably the friction. And the only problem in these structures is that these bearings, they cannot live for a long time because you keep shearing, and then at some point you have again a contact of three, let's say of two counterclockwise moving ones, and then they have frustration, and then the system breaks again. So we have already here the concept of frustration. Frustration means that you are unable to maintain this slipless situation. And I will come in more detail later. So in order to create such bearings, you have, okay, first of all, let me show you some other, these are experiments which are made in which you rotate, you have here a lot of small discs which have some black line to watch with a CCD camera rotations. So you can monitor the rotation of each individual disc by looking at these movies with CCD cameras. And then here this part is fixed and this part is moving slowly, this ball. And while moving, your particles exert some rotation and you get these kind of bearings along this created shear band which appears at this region. And you can then study the amount of rotation, how many particles rotate in which direction, and you can find the distribution of spin. You see, this is now the number of particles which rotate with a certain spin. There's a peak at 0, so there is a certain amount of particles that do not rotate, and then you see there is a finite amount of particles which rotate with varying angular velocities. And what you see also here is a simulation and experiment on top of each other, so it's just to show that this can be done also numerically. Okay, so let me come a little bit to the let's say easy phenomenological things you can understand. The first thing you need to, it's trivial if you want, is that in such a system of bearing, every loop that you make of contacting spheres must be even, because it must be, evidently you have always these two kind of particles, clockwise and counterclockwise, so that the network that you make by connecting the centers of mass is a bipartite graph, like for heterosexual sex. You have always two types, and you can only connect A with B. So this is the contact network. And then in 2 dimensions, the situation becomes very simple, because in 2 dimensions, the angular velocity is always perpendicular to the plane. So there exists only one direction, and this has as a corollary that the tangential velocities at every contact must be identical. And so there exists only one solution, which is everybody has the same tangential velocity, and the only thing you can change is the value of the tangential velocity. You can make it faster or slower. That's all you have as degree of freedom. The situation changes considerably when you go to 3 dimensions. Because in 3 dimensions you have, of course, also even loops, but now the angular velocity can point in any direction. And I will make a very small calculation to show you this let's say, extra degree of freedom. So imagine we create now a loop by adding one bead after the next to a chain and later closing the chain, okay? So the first at each contact, the tangential velocities must be the same. So at the first contact between particle 1 and particle 2, tangential velocities are the same. I can write the tangential velocity also at angular velocities. This is like this. I can put this on the other side, and I get this relation where R12 is the unity vector connecting the centers of mass of 1 and 2. So that means that this vector here is parallel to this vector. They're collinear. And so there exists a constant, which I call alpha 1, 2, which is constant at the contact between 1 and 2, which is free. You can write now, because you see these are parallel to each other, so this vector is alpha times the other one. So I can introduce this extra freedom, degree of freedom. And now I put the next one. You have 1, 2, and the third one, number 3, and number 4, number 5. And then now the j's particle in the chain, now it's just the composition of this rule more and more. So you see that you have a negative sign, so at each new particle you have to change the sign. So you have here you have -1 to the j, here also. Then this is the first part, and then you have the sum of all the alphas. So at every contact you get a new alpha, okay? And now I close the chain by identifying j with 1. So this gives me this equation here. And this equation has to be solved. So the first thing you can see to solve the equation is to set n even. This is, as I said already, the loops must be even, because if n is even, then this becomes 1 and then the two terms cancel. And the second thing you need is to make that this part here is 0. So this condition to be 0 can now be fulfilled in many ways. One possible solution I show you here, I can define the alphas as being just the sum of the radii of the two particles in contact multiplied by a constant c. And this constant c now becomes a new freedom, you will see, because now I can show that this is correct. I can now insert this alpha here in this equation, and then by knowing that the sum of all the radii, the sum becomes 0 because it's a closed loop, you can see that this becomes 0 here. And so this is the solution. So at every, for every loop, you can now choose another c, certain c, and this c will give you a new solution. So you see, in 3 dimensions you have more degrees of freedom, and this you can also show more generically, that this condition that I showed you here, this condition here, in fact, R3 is a vectorial equation, there are 3 equations. So you have 3, let's say, constraints, and so you can say, okay, if I have a chain of n particles, at every particle I add one parameter, but then I have this extra constraint, so you can count the number of degrees of freedom, and when you do that, and the loop is not coplanar, but it's let's say, then you can show that a loop of size n has n continuous degrees of freedom. And this can be then realized, so I should say that every solution in which every set of angular velocities which fulfill this is called a bearing state. And so what I'm shown is that in 2 dimensional there are only very, very few bearing states, and but 3 dimensional bearings are extremely rich and have a lot of degrees of freedom, and so a lot of different bearing states. So this can be used in practice. For instance, now if I consider the simplest case, which are systems of loops of size 4, the simplest you can get is 4, yes, that I can now define invariants which correspond to these different fixed, let's say, freedoms. I can fix these degrees of freedom by defining some invariants, and the invariants which I choose are this B and this H. B is some kind of overall momentum, and H is some kind of overall angular momentum of the system, more or less. And what I can now show is that these two, B and H, they cannot be changed. They are invariants. They cannot in time. So if you fix B and H, the system can only evolve with this fixed B and H. You cannot change B and H during the dynamics. So I will give you some more details. So this is for n equals 4. If I take n equals 6, then I have more invariants. No, means that every loop in my system is size 4. I have a big system, and every individual loop, not more than 4. This is the simplest case. Of course, I can have. Yes, okay, I've decided that I will only consider loops of size 4, but I could also later, I will show you examples with loops of size 6.
But in practice, you do not know how to do something like that. No, if I try to do it.
Well, the simplest case is a cubic lattice, or square lattice. I take a square lattice, then you have every loop is size 4, for instance.
No, they cannot go up, or I don't understand why not.
No, in the square lattice, you have always 4 touching spheres.
Okay.
Yes.
You mean the minimum one?
Yeah. Oh, everybody is 4. Minimum you can deal is 4. You cannot make smaller than 4. It's the simplest case. And in this case, I have a bearing in which every loop is size 4, because it's simple. I mean, of course, you can make it more complicated, but just to show the simplest case. And in this case, I can define.
And this is just for 3D.
No. This is true, yes, in 3D, yes, of course. But
higher dimension.
At higher dimension, no, it's not true. Higher is more complex, yes. So I give you some explanation of this B and H. So if H is 0, then you have, and B is different from 0. The B is a vector. Then you have a situation in which all the angular velocities point parallel in the same direction of B. And if B is 0 and H is different from 0, then you have a hedgehog situation in which the center of mass is fixed, and then all the others rotate around axes which pin into the center of mass like this. And all possible configurations are combinations of these two things. I mean, if you have arbitrary B and H, then you have a combination of these two states. Yeah, like a 3D board, yes, exactly. Okay, and so I can show that if I now give you B and H, I can tell you for every single bead or every single sphere, what is its angular velocity. So here, this is the angular velocity that you get when if you have a fixed B and H. M is the mass of the system, I is the moment of inertia, and x is the distance of this specific particle from the center of mass. So this is completely determined by just these two values, B and H. And now I will show you a small movie. So here I have a random initial configuration in which I have now, at the beginning, there is no force between the particles. So they can move easily because there is no friction. And then at some point I will turn on the friction, yes? And then the system, of course, has first dissipation because it's a friction, until they come to a state, a bearing state, in which the slip is 0 everywhere. So, and then we'll see what happens. So here you see, at the beginning, it's just, they're just rotating without friction. Now, when I come to 0, I turn on this friction, sliding, and now they slow down because they have a friction between the particles, and at some point, they get into a bearing state, which in this case is a case in which all are parallel to each other. And I came to another movie in which I start now. First of all, what is interesting to see, what is consequence of this, is independent on the dynamics that you have, independent on the kind of force. If you have viscous force or constant force or Coulomb force, independently of that, you will always attain, after finite time, the bearing state in a finite system. Yeah? So here's an example of two different such dynamics. And now I show another movie. Here I start now with a bearing state where everybody is parallel, and then at some point I will stop the one particle in the center, and this will then produce another bearing state. So here we see, first I have this bearing state, and then I block a sphere at some point. And now you see they slow down, of course, because of the friction. And after some time, they reach a state which is such that it's a hedgehog situation. That means that H is equal different from 0 and B is equal to 0. Okay, so this is just to illustrate the situation. And of course, you can always, this I will not show, we can also make experiments. Yeah? And here we did, this was done by Dominik Steger, by the students. So you can have several spheres that you put in contact, and then you rotate. I will rotate here with a motor, and then you see that everybody is going to rotate. And you can use this also as a how you call this in English, engrenage, to improve it's caixa di cambio, gear system. A gear system, you can, sorry, oh my God, this is I did something wrong. No, yeah. You can, for instance, here you can apply a very small angular velocity, and if you have a right combination, then you can have here a very high angular velocity. So you can change the angular velocities depending on the positions. Okay, so far now the situation of three-dimensional bearings. And next, I would like to talk about frustration. So frustration between bearings is, of course, very common. As I showed you in my first example, whenever you stop one wall, you force the other ones to stop also. So here, I will consider the situation in which I have on the bottom, everybody at rest, no rotations. So this is like the trivial bearing state in which there's nothing happening. And on top, I have now a bearing state where you have the clock turning clockwise, counterclockwise, clockwise, counterclockwise, alternating, yeah? Here on top. So these two bearing states are incompatible. Yeah? And I will study two different types of force between the rotating particles, the tangential force. I will consider viscous forces. Viscous forces mean that they are proportional to the velocity difference. Now you have two tangential velocities, and if they are different, then you have slip, and then you have a so-called viscosity, which I choose randomly between 0.1 and 1. Yes, I put some randomness in the system to make it more interesting. So not every contact is the same. There's some, and so this is a linear law, eta times the difference. And then the second kind of force I will consider is the much more realistic force between solids, namely the Coulomb force. Coulomb force is more complicated because there exists static and dynamic Coulomb force. Static means that when the particles are at rest, which means, well, let's say, if there is no relative velocity between them in this case, then they have you need a certain amount of force, yes, to start moving them. And dynamic friction is simply that when they are moving with a certain velocity against each other, that there is a force, but this force is not proportional to the velocity, it is proportional to the normal force. This is a Coulomb friction. It's a classical Coulomb situation. And we'll, of course, compare the two, and this will be very interesting. So, just some numerical details. So we have to calculate these things, and I will show you just how we do this. So I will use two different numerical techniques and show that they give the same result. One numerical technique is some molecular dynamics, if you want, which has a sophisticated name, discrete element method. But in reality, it is the same thing as molecular dynamics, except that you introduce this Coulomb friction, which in molecular dynamics usually is not done, because molecular dynamics is done for atoms, and you have Lennard-Jones potentials, etc. So these people here, Kundal and Struck, they are engineers from Minneapolis, which have invented a way of introducing Coulomb friction in molecular dynamics, if you want, and so this is now called discrete element method. So just as a name, but for everybody, a physicist, it is the same as MD. And the technique is very sophisticated because static friction means that the two particles are connected to each other until a certain force pulls them apart. And so this is done technically here in a very, let's say, dirty way by attaching a spring between the two particles, and the spring is broken when you reach the static friction limit. This is what is written here. So you have here a spring with the spring constant K and extension psi, and if this exceeds a certain value given by the static friction constant, then you break the spring and then you are free. So this is the trick to implement static friction, and dynamic friction is rather easy to implement. This is done here on top. You just have a friction constant which just reduces the velocities accordingly, because here in this case, since we have no real external pressure, the normal force is a constant. Okay, this is one technique. The other technique, alternative to this, consists in minimizing the dissipated power. So the system is dissipating all the time, as long as, if there is some slip, and every slip contact dissipates energy, and this dissipation is given by, power of this is given by force times the relative velocities. And so what we do is we look at the gradient of this and minimize the power of the entire system. So this is a minimization procedure, and then depending on if we take viscous contact or Coulomb friction, we have a different law, but this is just very technical. So just to tell you, we have these two completely different approaches, and we have to be assured that they give the same result. So let me talk first about two dimensions, which, as we have seen, is easy and interesting, easy case. So in two dimensions, yes, we have the two cases, viscous friction and Coulomb friction, give quite different results. In case of viscous friction, viscous forces, we have a continuum between the two states. Here, these are the two bearing states, and between the two, you have a slow change. Every contact has a certain dissipation, yes, and so this is there is no well-defined interface. Yeah? While if you do Coulomb friction, you find a very sharp interface between the two bearings. They seem to have 5 minutes. Okay, we have two bearings which, and this interface that you have can be shown that it is a minimum cut. That means it is the line that goes from left to right, along which the sum of the friction constants is minimum. It is the same problem as the directed polymer problem. It's the same problem, yeah, it's a famous problem that everybody knows from statistical physics. So you can prove easily that if you have this Coulomb friction, you get this minimum cut as interface. So far, 2 dimensions, so I have this very simple situation. And now, let's go to 3 dimensions. So in 3 dimensions, we thought, oh, let's look at the minimum cut as the solution. And you take the minimum cut, it is a 3x3 system, and you look at the minimum cut, and you now apply the algorithm of minimizing the power or the molecular dynamics, and you see that the system continues to let's say, to be, it comes to a state in which it has less energy, less power dissipation than in the case of a minimum cut. So there is a solution. The solution is not the minimum cut, but it is, let's say, different. And this is for the 3x3 system in which it is possible to calculate exactly the minimum cut because the system is very small. If you take a larger system, like 10x10 or 32x32, then, or the cube is a cubic system, 3x2x3, then it is not possible anymore to calculate the minimum cut. But you can see still, yes, that the system does not produce, when you look at the system, it does not produce a clear interface, but it produces some 2 regions which are the bearing state, and in between there is an interface region which consists of a lot of different clusters that each has some other bearing state. And the interesting thing is that here you see the gray lines here, they're difficult to see, are all contacts without slip. So every single particle, this is now spheres in 3 dimensions, every single sphere is connected at least at one contact without slip. And then there exists a very few paths, this is the green one, along which every contact is slipless. It means you can connect from one bearing to the other by going along a path which has no slip. But nevertheless, of course, the system has slip contacts, and of course there is dissipation in some places, yes? And of course, since in 2 dimensions we have shown that there is no way to go from one end to the other without slip, because there is this interface, it's clear, you can immediately follow that this line, this path that goes through the system cannot be in one plane. It has to be in several planes, because if you were in one plane, then you would have 2-dimensional connection. So you can actually see here, these are the green planes through which each of these corresponds to another green line through which this path goes. And the distribution of the dissipative power per contact is extremely large. I mean, there exist some contacts which have a lot of dissipation and some others which have very, very few dissipation. So this is a very novel kind of interface between 2 states, which is rich due to the fact that in 3 dimensions you have so many degrees of freedom and allows so many possible ways of making, let's say, bearing states. So this was the main result that I wanted to show. And I would like to just flip another small work before I finish. I have 3 minutes, I guess. Namely, one can also study, I remember, and I showed you the movie of this experiment, these spheres were hollow. And the reason why they are hollow is because they synchronize faster when they're hollow than when they are full. And this we kind of were able to show in the following piece of work. Namely, you can, if you look only at viscous forces, then the equations are completely linear. You have a system of linear equations. You have for every bead, yes, you have that here the inertial times the acceleration, angular acceleration is the sum of the torques. It's a classical equation of motion of rotation, yes? And so you can insert now this linear law. And what we now checked is what is the effect of the inertia of the individual sphere or the individual disk. And this you can control by an exponent alpha that you do between mass and radius. So in 2 dimensions, for instance, if the exponent is 2, then you have a full disk. If the exponent is 1, then you have an empty disk. You have a hollow disk. And what you can show now, and I don't want to go into too much detail, is that this system of equations synchronizes fastest when alpha equals 1. This can be done because the system is linear. You can do this kind of a perturbation analysis. So I don't want to go into details because it goes back to Pecora, who invented this technique. Look at the eigenvalues of these matrices of the perturbations, and then the ratio of the largest eigenvalue divided by the second eigenvalue, it minimizes at the point at which you synchronize faster, and you can see that this occurs here at alpha equals 1. So what we see from this is that the dynamics depends on the inertia of the particles, and it is the best to use hollow particles. And this explains actually a little bit why in watches, in Swiss watches, they don't have full disk, but they have always rings, because they synchronize fast. Of course, also you have less mass to move, so it makes a lot of sense. Okay, I guess my time is over, and thank you very much.
Thanks a lot, Hans. Very nice talk. Questions, comments? So, is for the hedgehog mode or the hedgehog theory, is it possible that all the particles has the same radius, or you have to have particles of a different radius?
I know you can have arbitrary radius. Yes, yes. I mean, I showed this cubic lattice because it's so simple. Everybody is the same. But in a generic bearing, everything I said before about the degrees of freedom and about this invariance, everything is true for arbitrary size distribution. Actually, I didn't show my full seminar. I have more. And there I show you, I have cases in which the distribution of sizes is power law. And if it's like that, then you can fill the space and you get this kind of Apollonian situation, yes.
Is there any relation of this with this sphere packing problem?
Sphere packing?
Yes, because how you pack a sphere, right?
No, because I'm only considering rotations. I mean, my system is already packed. And actually, the density, how dense the packing is, doesn't play any role. You can make it denser and denser by putting more and more particles inside if you want. So the only interesting here is, the particles don't move. They are static and they only rotate. Yeah.
Okay.
Good. So.
I wonder, probably you know something more, the underlying physics somehow, no? Because after all, what you have a system that turns out to be the most effective possible to distribute energies, and you have some constraints.
Yeah.
And well, is there a more general formalism that you could think about or something like that? Because that's your idea of your problem, right?
Well, what can be done to study this propagation is the so-called participation ratio of when you in the synchronization business. You can ask how much of each particle takes over the kinetic energy when you synchronize. And this, when you can show, is when the participation ratio is evenly distributed, then the synchronization is fastest. This is a theorem It also goes back to Pecora. Actually, I do have some I guess. Yes, this is a participation ratio for different values of alpha. And you can show when the alpha in which the synchronization is fastest, also the participation ratio is more evenly distributed.
Suppose if I think each wheel, each ring has somehow a rotor is a certain size, which corresponds to the rotation that you have on it. And then you have a nearest neighbor's contact. Then I have a scenario that I could think in some sort of thinking spins in evolution such that you go or not. There is no contact with that.
No.
Because each ring, you have some rotation, so you can think as a rotor, and then is in contact with another rotor.
One ring will automatically impose the next one.
Yeah, the next one is like an antiferromagnetic.
Yes.
And now what you are saying is that but the speed, because you have somehow friction, these spins can decrease the size, the rotor. You can rotate less, the other one less, and give it to the other one more thing. So it's like it's not.
What matters is not how fast you move, but the direction of the angular velocity. Because I can always increase all velocities by a constant factor. But you see, what is fixed is the relative angular velocity between neighbors.
Yeah.
But then I can, of course, have a global increase. I can increase everything if you want, or decrease everything. But when I have, let's say, two loops in contact, then one loop determines the neighboring loop.
Yeah.
Because you have this contact.
But when there is friction, what happens with the velocities? The friction, what does not try to decrease, die?
The friction will eventually slow down everything.
Yeah.
And if you have frustration...
But slow down, but it goes to another one, right? Or go to internal degrees of freedom that you're not in your game.
No, everything slows down.
Yeah.
You dissipate energy.
So if you say that all the energies are just a rotation and friction, so you are only changing this size of, these rotators. Speed,
yes,
right?
you change. Yes, you become the angular velocity becomes slower when they have friction, and until they have not reached a slipless situation, they will continue slowing down until they reach a situation in which the velocities, the tangential velocities are the same, and then they stop losing energy.
These two rotors stay exactly the same.
Yeah, when they have
amount.
That's right. When the tangential velocities are identical, then there is no energy loss anymore.
Yeah.
So the system, as long as the system is frustrated, you have to constantly inject energy into the system, unless it will stop completely.
This is a crazy question, but suppose you invented a dynamics where you place, let's say, a random walker on the circumference or on the surface of a sphere or a circle, and when it makes contact with the next object, it jumps onto that one. And now you can imagine a kind of diffusion process.
Yes, I can show you this. I can show you this diffusion process at the end. Here you have this. Here, this is what you mean, probably, yes?
Yeah, tracing.
Yes. Let me see. Here you see, this is the diffusion. This is rotating, you see, it's rotating, so the particles are driven by the rotating disk. But when they reach the contact, then they can go to the next one. And due to the fact that here I have a power law distribution in sizes, I obtain a situation in which they never fall into a hole, because otherwise it could be that they fall into a hole and never move.
Okay, so, you have anomalous.
And then you get actually a super diffuse Richardson law in this case, because of the fractal structure of this situation, yes.
Thought everything. Okay, let's make some again.
Sure, thank you.
Our next speaker is very bachelor. Murray, is he online? Can you hear me? I cannot hear you.
You hear me?
Yes, now we can.
Okay.
So, good morning,
Be here.
I suppose.
Hello. Let me share my screen. Hopefully my internet connection is strong enough. It's just the Wi-Fi.
Please.
Is everything okay?
Yes, please go ahead.
Yeah?
Yes.
All good? Okay, I'll make a start. So thanks very much for the to the organizers for giving me this chance to talk here. So as you can see, I will talk about the imaginary world of free parafermions. And the talk is really based on a paper that appeared on the archive yesterday. So it's very new work, but it's work that we've been, that has been underway for several years, in fact. So the outline of the talk, I'll just make some historical remarks at the start, and then I'll be really concentrating on a particular free parafermion model. I'll explain what they are, and I'll talk about something in the eigenspectrum called exceptional points. So let me go to the historical remarks. So as you can see here, this is a photo of Chico from, I'm not sure if this photo was actually taken in 86 or 87, but that was the time he was in Canberra at the Australian National University. So it's a long time ago now. And these were particularly exciting times. As you can see here, I had 3 publications with Chico from that time. They were exciting times because this was when, you know, we had sort of exactly solvable models. We had this link to conformal invariance and operator content in the finite size part of the eigenspectrum and so on. So, and of course, actually from time to time, people ask me, you know, who was my supervisor? They assume, you know, it was Baxter, but they could equally well ask, you know, was it Chico? But in fact, it was Barber, Michael Barber. So let me jump to here. Here's another early photo of Chico. You can see, I'm not exactly sure, and I think I'll have to clarify this with Chico, exactly when this was from. I went to Bonn in 88, possibly 90, and also possibly 92. So I'm not sure. He will know. So, and of course, as Herman said in his talk, Chico went to China, and I was, as he said, also there at that conference in Tianjin. And this is when Chico came to Chongqing in 2013. Yeah, that were very interesting times as well. And then I just want to say from that trip to China, in particularly the one in, I think Herman said 2008 or 2005, Tianjin, a lot of people there mistook Chico for Robert, excuse me, De Niro, okay? So that's kind of a long-standing joke. And in fact, I think even Chico signed a few autographs there as Robert De Niro. So let me get to the topic of my talk. So the building blocks of the model I'm talking about are these Zn operators, okay? So for n equals 3, they're 3 by 3 operators, and they're a natural generalization of the Pauli spin sigma z and sigma x. And that they obey this, what we call sort of parafermionic algebra, as you can see here. These are also called the shift and clock matrices. So the Baxter-Fendley chain is a model that was proposed in 1989. And for a long time, nobody seemed to care much about this model. And you can see it's a very simple Hamiltonian. For n equals 2, it reduces to the Hamiltonian of the quantum Ising chain. Okay, that's well-known and widely studied model. And for n equals 3, you can kind of consider it as a half of a Potts model, okay? But the key point about this model is that it's non-Hermitian, okay? It has a complex eigenspectrum. But nevertheless, for example, the ground state energy is real, and you can calculate it. And that's what I'll say shortly. That's what Chico and I did. But just let me just show you the expression for the eigenspectrum here. Okay, so it's just a very natural generalization of this free fermion eigenspectrum here, which everyone knows really well, okay? It's just that the prefactors in front of these quasi-energy epsilons are all complex, okay? But of course, in some cases, they can be real as well if the pk is equal to 0. So this gives all of the energies in the eigenspectrum. The energy levels are known exactly. And this was originally a numerical observation by Baxter, as I said, in 1989. And I've got some of the key publications here. And the model actually originates, in exactly solvable models, nothing is really new. It's very hard to find something new. This model really sort of originates in what's called the Tau2 model. So it's a classical two-dimensional model, and this model can be obtained as the Hamiltonian limit of that model. So, and then why have I attached Fendley's name to this model? He actually derived this eigenspectrum from a generalization of the Jordan-Wigner transformation, okay, namely the Fradkin-Kadanoff transformation. This really started to make this model sort of well known. It started to draw some attention. So Baxter jumped on it again, Perk and Yang. And then in 2019, Fendley developed a sort of more algebraic framework for it. And then Chico and Pimenta jumped on that and wrote down some more, some other interesting, exactly solvable free parafermion and free fermion models with multi-spin interactions. So time is short, so I've just said I'll just talk about the symmetry in the eigenspectrum. It's just a Zn. And these non-Hermitian Hamiltonians are very worthwhile studying. So here is the eigenspectrum. you can see, so here's a picture of the eigenspectrum, which are the little black dots here in the complex energy space, if you like. So the ground state energy is here, and everything else is excitations. So it's a picture in the complex plane, and you can see that here as well. So here is the eigenspectrum when this parameter lambda is equal to 1, and these are the quasi energies here. Okay, the building blocks of the whole eigenspectrum, and we're comparing with exact diagonalization there as well. So the motivation for this work very quickly is that we did a study of this model, and we saw that some of the correlations, okay, were not behaving in the normal way. They were diverging. So that kind of says there's something interesting happening here. And we're using the publication with from 2017 with Chica, where we wrote down the solution and used it to calculate some properties of the free parafermion model. So here's the solution for the quasi-energies, and these variables k, they have to solve this particular equation here. And the point is, what you can do is you can extend. So I'm saying the solution also applies to complex values of the coupling. Okay, everything holds, the expression for the ground state energy and so on. It's just that the quasi-energies become complex, and for certain values in the complex plane, they become complex conjugates again, and you have a nice eigenspectrum and so on. So I'm saying that exceptional points are very important for non-Hermitian systems. They're where two eigenvalues or more become the same, okay? And they're very important for investigating the topological phenomena, okay? So, and it's a huge topic, and I'm saying what we've done is we've located exactly the exceptional points in this model, okay? So there are exceptional points when the two quasi-energies come and touch each other, right? They're the same. This leads to what we call a Hamiltonian exceptional point, okay? So that's a degeneracy in the eigenspectrum. And I'm saying we can use this exact solution to work out exactly where these exceptional points occur in the eigenspectrum. So here we're solving this equation for small sizes L, and then we're comparing with the zeros where two of these quasi-energies become the same, and they occur precisely at the solutions of this equation, okay? There are some what we call non-trivial exceptional points you can see here, and then I'm saying we can use this exact solution to work out exactly the values of lambda in the complex plane where the exceptional values are. So, and you can see actually that as the system size increases, they are actually on the unit circle. So here's zooming in more closely here. So let me just go to the concluding remarks because time is short. I can't show you everything. So I'm saying that we have located the quasi-energy exceptional points in the complex plane. Numerical tests confirm they correspond to Hamiltonian exceptional points, and also confirm that the corresponding eigenvectors coalesce. There are other degeneracies in the energy spectrum, but they are not exceptional points. And although in the complex plane, exceptional points can influence properties such as the correlations along the real axis. And we think this is why we were seeing, for example, diverging correlations for n equals 3 and so on. And I just refer you to this paper on the archive, which was, as I said, posted yesterday. And I'll just conclude by saying happy birthday, Chico.
Thanks a lot. Questions?
Hi, Murray. You are solving the equations for how many particles or the solutions? How far can you go?
You mean the exact or with just the numerical checks?
Yeah.
So we can do everything exactly. So in this paper with Chico, we use what was called a large L expansion. So you can have approximation for the roots of these, well, for the K for large L, and you just make use of that.
Mm-hmm.
And then we just try to check everything numerically as far as we can.
Yes, it's 50, yeah?
Yeah. He was 50. Yes. So this is a kind of this circle in the complex coupling plane is a sort of end state generalization of the Li-Yang sort of singularity for the Ising case, which is a special case of this model. So it's like that.
Mm-hmm.
That's what we think.
Hello, Mari. It's Chico.
Yeah. Hi, Chico.
Mari, it's a pity you couldn't come here, but anyhow,
yeah.
You had the opportunity to come, so that's was.
Yeah. I'm hoping to certainly go at one point. I promise that.
In the 80 you come, right? Anyhow, Mari, let me understand. This exceptional point, when you say the vector coalesce, this means that you become like a Jordan cell, disappear one of eigenvectors. What is it? Or is your Hamiltonian start to have Jordan cells there?
I'm not sure if I can answer that. I'm just saying that at such points, the two of the eigenvalues become the same, and
but they still has two eigenvectors. Suppose two, but they are still eigenvectors. I mean, you don't lose.
Yeah, I can't really say much more than that at this particular point.
Okay, so somehow you thought out many places where you combine with this circle exclusion places that you have the same energies, but you said that some of them have some behavior, others not always.
That's right. Yeah.
And
like if you can imagine the eigenspectrum here, right?
Yeah.
You can see as you change the coupling, all of these eigenvalues are going to be shifting around, so they overlap. But I'm saying not all of them correspond to exceptional.
Okay, nice. There's a motivation to read your new paper.
Yeah. I strongly encourage everyone to have a look at our new paper.
Okay, bye-bye.
Okay, thanks everyone.
Thanks, Murray. I have to move on. Our next speaker is Rodrigo Pimenta from University of Manitoba.
Hello? Okay. All right, so let me first thank the organizers to be here in this such a nice opportunity. I have been working, so I'm going to speak about this new kind of free fermionic quantum chains that I have been working with Chico for about 3 years now. It has been very nice and I'm learning a lot about it. This one that I'm going to present today, it's a joint work with Chico and Jasko Sirker from the University of Manitoba. And so it's a quick talk, so I'm just going to give you a brief introduction, and then I'm going to show the Hamiltonian and some new effective inhomogeneous chain that we have been constructing, okay? So we all know that free fermion models are like usually Hamiltonians that are quadratic in fermionic operators, either complex or Majoranas, right? And the solution of such quantum spin chains goes back to the seminal work of Onsager, which was later simplified by Kaufman and Lipschutz and Mattes. And maybe one of the basic examples is the quantum Ising chain, all right? So the Hamiltonian is this very famous Hamiltonian. Here I'm considering a case where the couplings can change from site to site. So the term with the interaction, sigma z, are like the even couplings, and the term in sigma x is like the odd couplings, right? And when we do the Jordan-Wigner transformation, we obtain this kind of Hamiltonian, right? So it's a Hamiltonian that is bilinear in the Majorana operators. Okay, so the Majorana operator satisfies this kind of Clifford algebra, all right? And usually how we solve this type of spin chain, we find some linear combinations, right? So like, for example, we write creation and annihilation operators in terms of the original fermion operators, and we can show that the spectrum has this form, right? Like a sum of quasi-particle energies. And recently, a very intriguing Hamiltonian was introduced by Paul Fendley, because it's intriguing because it's a Hamiltonian that it's not quadratic in the fermionic operators, but nevertheless has a free fermionic spectrum, right? So it's this Hamiltonian here, this very simple Hamiltonian, like sigma x, sigma z, and sigma z. So it acts on 3 sites. And when we do the Jordan-Wigner transformation in this case, so I wrote here in terms of complex fermions. So we have this kind of, right, this tight binding term, but it's modulated by some number operator in the previous site. Or we can also write in terms of Majoranas. So in terms of the Majoranas, we have this kind of 4-Fermi Hamiltonian, right? And it's very intriguing because we look such kind of Hamiltonian and we would expect it to be interacting and not free. All right? And Paul Fendley finds a beautiful solution using integrability, right? So he is able to build some kind of generalized fermionic operators, but the problem is that these are no longer linear in the physical modes. So in particular, Wick's theorem does not apply, and we don't know how to compute correlations. And with Chico, we generalized Fendley's model to multi-spin and parafermionic case, as Murray mentioned in the previous talk. And the basic idea is that we consider let's say some generalized, here I'm going to consider only the fermionic case, and we consider the Hamiltonian as a sum of generators with some couplings, and the basic rule of this generator is that they anti-commute if they are close to each other, and they commute if they are far apart. And they square to their identity. And only using this kind of algebra, we can prove that the spectrum is of this form. So it's the sum of quasi-particle energies, right? And the important point is that these quasi-particle energies are actually the roots of some polynomials that are generated by a recurrence relation, like this one that I put here. So let me bring your attention to the fact that for like p equals 1, we have the standard case. So like the quantumizing chain, so this is second order recurrence relation. But for p bigger than 1, like the Fendley model, this is a higher order recurrence relation. Okay? And the quasi-energies are given by in terms of the roots of this polynomial. And let me remark that the fact that this is a recurrence relation allows us to study the spectrum very efficiently, including very large chains and disordered couplings. As if you are interested, you can take a look at this paper that we wrote with José. Okay. And so the models are integrable for any couplings, but we consider a splitting that is very natural because of this algebra, which is we split the couplings according to their parity, which means it's some kind of even and odd, but some generalized version of even and odd. And so this means that like for p equals 1, we write the Hamiltonian as lambda a, big HA, and HB, where, for example, we are summing odd couplings, odd generators, and even generators. And like for p equals 2, then we have 3 terms. Okay, we have like these analogs of even and odd, but for a generalized version. And let me just bring your attention to the fact that, so like for p equals 1, in the periodic case, which is not the one that we are considering, this operators forms Onsager algebra, and in the case p bigger than 1, we have a generalized Onsager algebra as it was shown by Yuan Miao. And so in this case, the representations are given by multiple Majoranas. So for example, the p equals 1 is the standard case. So we have the Majoranas interacting only with neighbors, right? So these dots are Majoranas. And as we move to bigger values of p, very interesting structures start to appear, right? So we have now for p equals 2, the Fendley model, we have like 4 firm interacting, right? And they get crossed with each other, okay? And like for p equals 4, we have a 6 firm Hamiltonian, and then we have this very intricate structure. And the nice thing is that nevertheless, they are all free, okay? But as I mentioned, unfortunately, Wick's theorem does not hold, and correlations are difficult to compute. So this is an interesting open problem. Here, we propose effective models that have the same spectrum as the generalized chains. And the price to pay is that the effective models have inhomogeneous couplings. Okay? And so the idea is the following. We know that the spectrum is given by the roots of this p polynomial, and we define some auxiliary polynomial that we call Q. And we take this polynomial to be the characteristic polynomial of certain anti-symmetric three-diagonal matrix. Okay, so we consider some three-diagonal matrix like this. And we compute the characteristic polynomial, which is given by this determinant. And we just impose that these two relations are the same. And so we impose that this determinant is equal to the Q polynomial. And we can and so by construction, we can then build a standard Ising Kitaev chain with this three-diagonal matrix. Okay, and it's going to have the same spectrum as the generalized chains. And so we can like solve by brute force, and we can realize that the solutions are not unique. But mathematicians have studied this sort of problem before, and they invented very efficient algorithms to find the three-diagonal matrix. And here we are going to use one that was proposed by Schmeiser in the 90s, and this is in this paper here. I'm not going to explain it here, but it's very easy to implement algorithm. And so as we vary the Hamiltonian couplings, we obtain different couplings, and this is a kind of typical result, okay? So in this picture here, I'm showing like the couplings as a function of the coupling parameters. And we can see that as we move in this parameter space, this couplings starts to change, and it's like predicting the phase transition, okay? So it's very nice that the algorithm gives us the point where the transition occurs, right? So for example, here for lambda less than 1, we have that the even couplings are bigger than the odd couplings, and when we go to the other side of the phase of the transition, we have the opposite case, right? And for these inhomogeneous models, we can compute correlations and analyze the phase diagram, okay? Because when we have like a standard Ising chain, we can use Wick's theorem, and basically what we have to compute is the 2-point Majorana correlator, and then we can compute everything, right? And the nice thing is that we found that the phase diagram depends on the number of the part of the number of generators, okay? And so here I put these results here, and so I consider like 3 cases, like for p equals 2, and the case where m, the number of generators, is a multiple of 3, the number of generators is a multiple of 3 plus 1, or the number of generators is a multiple of 3 plus 2, okay? And what we found is, and so if you remember, we divide the Hamiltonian in 3 couplings, right? Lambda A, lambda B, and lambda C, and we are analyzing the phase diagram in terms of these couplings, okay? And so here, what I plot here, like, let's say we fix one of them, let's say lambda C, and we vary lambda A and lambda B. We are compute this numerically because the quantum chains are inhomogeneous, and that's the only way we can do. But anyway, we can do it for large chains, and it's a very nice result because, so for example, in this first case, we have like transitions from disordered to disordered phases. But like for other kinds of periods, we have like ordered and ordered disordered, okay? And here we have like a more standard ordered disordered transitions, right? And let me just mention that like close to the axis, then we recover the p equals 1 case, which is the standard Ising case, okay? And yeah, so the message is that we can engineer effective free fermionic Hamiltonians with the same spectrum as the generalized models. And using these models, we hope that we can grasp some universal behavior beyond the spectral level, right? And something that we would like to do is to check if we can implement similar program for parafermions, right? And one very interesting problem as well is like to solve the periodic chain. So if we take this spin chain, right, and we put periodic boundary conditions, it seems like it's a very simple modification, but when we do that, we can no longer solve the chain, okay? And let me just mention that this is precisely the case where the Onsager algebra works. So it's likely that the best way to handle this problem is by analyzing representations of the generalized Onsager algebra, right? And yeah, and one nice thing is that it seems that because the phase diagram depends on the number of generators, there should be some kind of topological phenomena behind these models. But we don't know how to define topological invariance for this kind of spin chain, right? Because what usually people do it for quadratic Hamiltonians, and so it would be very interesting to be able to define such kind of invariance for these chains, okay? And so, parabéns, Chico, and happy birthday. Thank you.
Thanks a lot.
Okay.
Very innovative and interesting talk.
So I understood that you are making isospectral mapping, right?
Yes.
And given some Hamiltonian, you want to go to the three-diagonal one. Now, I've been checking myself that if you do naively, usually you have also complex term in this. So is there any condition on the spectrum why you have automatically real coefficients?
Well, in our case, these polynomials have real roots. And so...
No, but the spectrum is real.
Right,
So
right.
I give you the integers.
Right.
But I want to put in a three-diagonal form the Hamiltonian.
Right.
So if you apply the method of the mathematician you were mentioning, typically you have complex couplings.
Even if the...
Even very simple spectrum.
Right.
So do you know how to correct this? There is a technique, there is...
Well, the only condition is that this polynomial has real roots. If it has real roots, then the three-diagonal matrix have real entries.
No, it's false. It's false.
Okay, yeah, I would have to check more precisely, but as far as I remember in this paper...
Now you might have a three-diagonal term, complex term.
Okay.
Nevertheless, the characteristic polynomial is a real root.
All right. Okay. I see your point. Okay.
So typically, to do the inverse is not automatic.
No, it's not. Yeah.
So
okay. Okay. I understand. Okay. No.
So
all right.
I'm asking, you know how to do it?
Yeah. No. I would have to check and see. Yeah. But I will have to think more. Yeah.
Okay.
Okay.
Just to complement what Musa is trying to say, when you show the picture that you see these inhomogeneous couplings.
Right.
It was the inhomogeneous couplings or is the square of it?
This is the square root. And there is also one point because this algorithm is for a symmetric three-diagonal matrix. And to build quantizing chains, we need an anti-symmetric matrix. So we must be careful with this sign as well. Okay.
In order to have your free spectrum, right, and be integrable in some sense, you expect it to have conserved quantities, right, and a set of commuting observables to allow you to do that. Do you know what these observables are?
Yeah, so this is actually the way that Fendley solved this problem initially. So because of this algebra, you can build the charges explicitly. And so you put them in the form of a transfer matrix, and that's where this spectrum follows from.
Okay. Well, for the questions, let's thank the speaker again.
Thank you.
So the last talk of this workshop will be by Luis Ferreira from the house. Rodrigo, eu preciso do microfone.
Como é que eu mudo aqui?
Ok. Um teste, vocês estão me ouvindo? Estão? Estão me ouvindo? Ok. Ok. Boa tarde a todos. É um grande prazer. Oh, sorry. So it's a great pleasure to be here. I mean, and I thank the organizer for the invitation. Well, first of all, I would like to say some words about Chico and to Chico. You see, I think any physics or maths department would be very happy to have Chico as a faculty member, I mean. And we are, of course, very happy and proud. And it's very fortunate that we have him here. I mean, he's not only his scientific leadership, but also as a person, I mean, and this personal leadership that he's very human. And so it's a great pleasure for us. So Chico, happy birthday. And so thank you very much for everything you have done, not only here, but for the Brazilian science. I mean, that's a great thing. Okay. So the topic of my talk is hidden symmetries. I'll be talking about some work I have done, and at the end I'll talk about some unpublished work that we are still working. So I'll be talking about hidden symmetries in non-abelian gauge theories, okay, in 3+1 dimensions. So the real non-abelian gauge theories in 3+1 dimension. So these are the theories that describe the fundamental interactions of nature, like the weak and strong interactions of nuclear physics, and also electromagnetic interaction. Okay, so I'm talking about the symmetries of the standard model of the fundamental interactions. Okay, and there are hidden symmetries, and they're quite amazing. I mean, we are still exploring these symmetries, and we are very surprised with the structures that are coming out. And we hope that it can help understand some non-perturbative aspects of these very important theories, not models, you see. The main idea behind this is the old thing that you learn in electromagnetism, okay? This type of equation that the flux of some field through a surface is equal to the charge in the volume bounded by this surface, okay? The thing I'm going to show you that these type of equations are conservation laws, okay? You can write that equation as an isospectral evolution for some operators. Okay, let me call the attention. Everything I'll be talking here is at the classical level, okay, not quantum yet. We hope that we can go to the quantum, but the classical level is already very complicated. Okay, of course, if you have that, the eigenvalues of these operators are conserved in time. And the important thing is that it's a non-nether conservation law. These are non-nether charges. And the importance of that is the following. The nether charges come from symmetries of Lagrangians or Hamiltonians. So they map solutions of a given energy to solutions of the same energy. So you vary in a very small piece of the space of solutions, right? But these symmetries don't preserve the energy, don't preserve all the charge, in fact, of the theory. The symmetries associated to these conservation laws, they map quite different solutions into each other. Okay. Of course, this type of equation underlies gauge theories, especially electromagnetism. Okay. And also it underlies integrable theories. But what I'm going to talk about here is not an integrable theory. Non-abelian gauge theories in 3+1 dimension are not integrable, especially with matter fields, because what I'm doing apply to the full theory with matter fields also. Okay. But the point is that the techniques that we use here are similar to what is used in integrable field theories in 1+1 dimension, let's say. Okay. So we are going to use this to construct the conserved charge for the Young mules and then the hidden symmetries. Okay. So now what I'm going to do is something you are very used to. Okay. But I'll phrase things in a different way to put in the same framework that I need for higher dimensions. Okay. So, as I said, I need a flux equal to a charge. Okay. So let's start with the 1+1 dimensional case and take two fields, a matrix G and another matrix A, which is a one-form connection in space-time. Okay. And they are defined on any point of space-time. So we have two matrices. In fact, if you are in 1+1, you have two matrices here, one there. Okay. So you impose, given a curve, gamma, starting in XR and ending in X, you define this equation. And that's the holonomy of the connection here integrated along the curve. Okay. And it's equal to the value of G at the end point times the inverse of G at the initial point. Okay? That's the equation. And that's the equation I impose for any curve on space-time. Okay? Any curve. So, if it's valid on any curve, okay, and another thing is that I'm interpreting this as the flux coming out at the end points of the curve, and this is the charge inside the volume, which is now one-dimensional, because I'm in 1+1 dimension. Okay? So, as I said, it's valid on any curve. So, if you change the curve but not the endpoints, the left-hand side doesn't change. But the right-hand side changes because the curve changes. But the equation says they have to be equal. So, this equation implies that that holonomy is path independent. Okay? That's the main result coming from this type of equation. Now, if you Taylor expand both sides of this equation, okay, you get a local differential equation, which is this, relating the same fields, A mu and G. So A mu has to be a pure gauge connection, because since it's path independent, it has to be a flat connection. Okay? And that's the differential equation associated to this integral equation. Okay? So if you think of these as Maxwell equations, that's are the integral equation of electromagnetism, let's say. Okay? So since it's pure gauge, so the curvature is flat, but that is our good and old Lax-Sakharov-Sabah equation used in integral theories in 1+1 dimensions, right? But I'm not going to use this integrable aspect. I'm going to use this flux equal to charge thing, okay? So, just to show you how the charges are constructed, you use the path independence. And then what you have is the following. You take two curves, you start and end at the same points. Since the holonomy is the same, it means that the integral along this curve has to be the integral along that curve. So the Wilson line is ordered such that you start from here and from right to left. So you have u minus 1 to u, because I impose these boundary conditions. So you have the spectral evolution, isospectral evolution equation. So the eigenvalues of this Wilson line operator is conserved, and these are the conserved charge in these 1 plus 1 dimension theories. Okay, so that's something that I think all of you know very well, but I want to phrase it that way to go beyond, okay? So let's go to 2 plus 1 dimension, right? In 2 plus 1 dimension, take a surface, because you want the charge to be integrated on a surface now. So you scan the surface with loops starting and ending on a given point on the border, x0, right? But one important object here is the following, is the loop space. The loop space is a space of functions going from the circle S1 to the space-time, okay? Such that the north pole of S1 is always mapped on a fixed point x0. So, if you take this surface on physical space, you transform it on a path on this loop space. So the initial point x0 is the infinitesimal loop around x0. And as you move on, you move to the loops until the end point of this path in loop space is the border of the surface. So you take a two-dimensional surface and map in a one-dimensional object on an infinite dimensional space, which is loop space. Okay? So then it's obvious what to do. So what you do is to look for an integral equation such that the charge on this line is equal to the flux coming out at the end points. Okay? That's what we want. And then you construct the conserved charge using the path independence. Okay? That's the idea. So, the thing we want to do then, in any dimension, right, is this. You consider the generalized loop space now. If you have a space-time of d plus 1 dimension, you consider the loop space d minus 1, which are functions that map the sphere in the d minus 1 dimensional sphere to the space-time such that the north pole is mapped on the reference point. And again, if you have a volume, for instance, you use maps from S2 to the space-time. So you scan the volume with closed surface, and the volume becomes a path in this loop space. Okay? And then you introduce an integral equation. The flux of something B here on the border of this volume, which is the border of omega, is equal to the charge inside of it. Okay? And then, of course, since you have this integral, you use the path independence because you can change the volume without changing the border. And then you have the path independence, and then you have the isospectral evolution, right? For instance, in loop space now, you take a path starting and end on the 2 points, and you get the operator here like that. And then you choose another path, start and end at the same points, okay? And imposing boundary conditions, you get the isospectral evolution. So the idea is simple, okay? The implementation is difficult. So let's do it for non-abelian gauge theories now, okay? How much time do I have? Time? All right, okay. To do that, to construct these integral equations, what you need is the so-called non-abelian Stokes theorems. Okay, the non-abelian Stokes theorems for one-form connection is well known since the 70s, but for higher connections is something else. So we construct this many years ago, and is the following: take a 3 volume, okay, and you scan it with two-dimensional surface starting based on this reference point at the border. and these are labeled by zeta. And then each two-dimensional surface is scanned with loops, parameterized by sigma and labeled by tau. Okay? So that's how you scan the volume with two-dimensional surface and loops. Okay? Then the non-abelian Stokes theorem, you take a tensor, that's the two-form connection, right? W is the Wilson line for a one-form connection. We need that to keep control on how this thing transforms under the gauge symmetry, okay? But I don't have time to enter in these details. And then this side is the Wilson surface for this connection here. Is built from the view, the tensor, and the W. And that thing is the Wilson volume, which is given by this, okay? The upper script W means that this thing is conjugated by W minus 1 W. Everything that has the W there has the conjugation. So that's the non-abelian Stokes theorem that you needed for gauge theories, non-abelian gauge theories, okay? That's a mathematical theorem. Is valid for any rank 2 tensor and a one-form connection A mu, okay? Which is the one that gives the Wilson line W there, okay? Now, the integral equations for Young mu's now is easy once you have that theorem, because what you do is to replace the B mu nu, right, that appears on the theorem, by a linear combination of the field tensor of gauge theory and its dual. You have this now is the physical gauge field A mu, right? And that's the curvature, so that's the field tensor of non-abelian Young mu's theory. That's the covariant derivative in the adjoint representation. These are the Young mu's equations, and that's the Bianchi identity, right? And the currents come from the matter fields. Here I wrote just the spinors, but you can have the Higgs, boson fields, and so on, all inside this J. Okay, they're all there. So what I did, I replaced B mu by that, and then I used the Young mu's equations to transform that exterior covariant derivative of B mu to put the current there. Okay. So that's the non-abelian Stokes theorem. Okay. So this integral equation is a direct consequence of the Young mu's equations and the Stokes theorem. And when the volume goes to 0, to infinitesimal volume, you recover the local non-abelian, the Young mu's equations. Okay. The charges you take the integral equation on a volume on R3. Take the space-time is the Minkowski space. You take the space, which is R3, so that's the volume. And the border is a true sphere of infinite radius, at infinity, right? So here is the true sphere, which is the border of our physical 3 space at a given time t. Okay? So if you change the volume without changing the border, you get the path independence. And then you get the conservation loss, which are the eigenvalues of this operator. And you can calculate the charge as the eigenvalues of the surface integral or the volume integral. Okay? They have to be equal because this equality here is Young mu's theory. That's another way of writing Young mu's equation. Okay? These conserved charges, first of all, they are gauge invariant. This thing solved a problem that lasted 50 or 60 years in non-abelian gauge theories. Because if you take textbooks, right, on gauge theories, the way they construct the conserved non-abelian electric and non-abelian magnetic charge is such that they are conserved, but they are not gauge invariant. So they don't make sense physically, right? If you take Weinberg's book, for instance, he discussed that, okay? this problem. So this was solved 10 years ago on, by my PhD student Gabriel Lucchini. It's his thesis. And the charge, the number of charge, is not the dimension of the group like in textbooks, but it's the rank of the group. Okay? And also, they are independent of the reference point because everything here relies on this scanning of the volume. But you can change in a base point. You can change the base point, and what happens is that those operators change by, I pressed the wrong button. Here. If you change the reference point, those operators change by conjugation, so the eigenvalues don't change. And is independent of parameterization. That's an old problem, right? Because when I said you take a surface in space-time and map on a path in loop space, that's depend on a scanning. But you can change the scanning without changing the surface. So the physical surface doesn't change, but the scanning changes, so the path in loop space changes. But the physics cannot depend upon this change, okay? So at the end of the day, everything has to be independent of that change of scanning. And it is guaranteed by the path independence already, okay? I don't have time to discuss all the details here, but it's path independent, so it's reparameterization invariant. That was a breakthrough, in fact, okay? So they give non-trivial dynamical magnetic charge to monopoles, because if you take the textbook charge and calculate for the 't Hooft-Polyakov monopole, is 0. If you could do it for the Wu-Yang monopole, is 0, okay? And also they're not gauge invariant, but these charges are not. But they are not, so the 't Hooft-Polyakov monopole now has a topological charge and a dynamical charge, okay? Okay, the hidden symmetries now. So that's the thing that's not published yet, and that we are still working on. The hidden symmetries are the following. What you need is a one-form connection lambda, which is not the gauge field, the physical gauge field. They are parameters of the group. And an antisymmetric tensor, which is also parameter, and they are independent. This is not the curvature of that. Okay? And they live on the Lie algebra of the gauge group, the physical gauge group. Okay? If you take the standard model, is SU3 cross SU2 cross U1. Okay? That's where they live. Then what you do, you construct the Wilson line associated to that connection, which I call omega, which is the holonomy. And V is the holonomy of this connection, which is a connection in loop space, in fact. Is built out of this tensor and the holonomy of lambda mu. Okay? So the group elements are these V's. And what you do is the following. Now comes a non-trivial thing. You take the relevant loop space in 3+1 dimension, which is this function space, this infinite dimensional space, which are the maps of S2 into the space-time, okay? So it's an infinite dimensional space. Now you choose one loop in this thing. But now you don't have to worry about reparameterization. You can change the reparameterization, change the loop, so you change the group you are building. That's funny. We're still trying to understand it. And the thing is, if you take this holonomy and take now two sets, lambda and rho, lambda prime and lambda 1, rho 1, lambda 2, rho 2. So you build V for then V1 and V2 associate to these lambda 1, rho 1, lambda 2, rho 2. Okay? And you multiply them because they are matrices. And then you build another matrix V3. This product is a group, is a Lie group product. This product builds up a Lie group. It's quite easy to prove that. Okay, so it's a very simple structure. But this Lie group is infinite dimensional. Okay? And the composition law is such that these connections, the gamma 1 and gamma 2, right, composed in this way. If you multiply V1 from the left, then the connection associated to V1 is conjugated by the group element of V2, and you add L2, okay? That's the product law. It's a Lie group. It's an infinite dimensional Lie group. And the hidden symmetries is a left and right symmetry that comes the following way. Take the integral equation of Young-Mills, okay? This thing is a group element now, but it's associated to the physical gauge field, okay? And its curvature now. So what you do is multiply, for instance, from the left by an element of that group, and you transform this group element associated to the physical gauge field, and you define another gauge field, okay? And the composition is the composition of that thing. And if you multiply from the right, it's the same thing. You go to another one. So these transformations map solutions into solutions of Young-Mills theory. So for instance, if you start from the vacuum, you can build the Tooth-Polyakov monopole using this transformation. If you take go to Euclidean space, take the vacuum, you apply one of these group elements, you get instantons, for instance, after the vacuum solution. Okay? We are trying to understand a lot. This is what happens in 1 + 1 dimensional integrable theories. I'm not saying this is integrable, it's not, right? But what you do in 1 + 1 dimensional, how do you build the soliton solutions in 1 dimension? Use the inverse scattering or use the dressing, which is a gauge transformation, right? So you start from the vacuum, you build 1 soliton, 2 soliton solutions. I'm saying that the mathematics is the same, but the physics is quite different, because this theory doesn't have, even though the group element, the group is infinite dimensional, it might not be infinite enough to make this theory integral, and I don't believe it is, okay? But the mathematics is very similar, okay? So these are the symmetries. And so these are some high reference. Sorry for how much time.
Thanks a lot.
Okay.
Two questions relative to the charges. So in non-abelian case, even if you do not have quark, the gluons has charge. So you find that it's non-zero anyway.
It's non-zero.
Okay. The second one is with this argument geometrical, which are very elegant, robust, and so on, can you understand the quantization of the charge?
For instance, let's take the electric charge in electromagnetism, right? Let's take a simple case, which is there. You can put the electromagnetism. But when you go to Maxwell theory, a lot of mathematics trivialize here. But if you take these integral equations in a space-time which is closed, four-dimensional, the four-dimensional space is closed, the electric charge comes out quantized.
Because the usual Dirac argument is for the magnetic charge.
Yeah.
You have a different way of getting.
Yeah. So it comes from topology, but I don't know how to quantize the thing in Minkowski space. But if I take a space-time which is closed, a four-dimensional space-time which is closed, then the electric charge is quantized and the magnetic charge is quantized. But this is not a result by us. It was known already that when you take these integral equations in closed space-time, you get quantization of thing. But the argument is the same. You get it quantized. We have it written down in this paper 10 years ago by my students. This thing of the symmetries I'm doing with this same student, Gabriel Luquin, now he's a professor in university, and another PhD student, Henrique Malavesi, right? But yes, you can get the quantization. In the case of, if you take the integral equation here, so if you, the beta is associated to the dual. So if you take a space volume, this is the electric field. So you put beta equals 0, and then you have alpha. If alpha is put to 1, you get the quantization of the charge, the magnetic charge. The magnetic charge is not that difficult to quantize, but you have to say that in the case of alpha equals 0, yes, you get the quantization. In fact, we did that. We calculate this charge for the Truth-Polyakov monopole, and they are dynamically conserved but quantized. And they are, funny thing is that they are not associated to the homotopy groups like the topological charge of Truth-Polyakov monopole. They are associated to weights of the group, the gauge group, that appear in the Nunn equation. You know, the Nunn equation is the to calculate instantons, you use the ADHM construction, Atiyah, Drinfeld, Rich, and Miami. So you have those. When you go to Minkowski space-time, the equivalent is the Nunn equation, Werner-Nunn equation. And it's like a Lax equation, right? And there appear some weights. And that's exactly the charge of our monopole. So, in fact, when they plot this way, they come the skyline diagram. So we reproduce this skyline diagram with our charge, the magnetic charge.
Yeah, well, simple question. You said there is an infinite dimensional Lie algebra.
Yes.
Do you know what is the Lie algebra?
In 2 plus 1 dimension, we have it more clarified. In 3 plus 1, I think if I would have to guess, I know it's a Lie group and it is a Lie algebra. The structure, if I would guess, is a 2-loop Kac-Mood. In 2 plus 1 is the Kac-Mood, right? In 2 plus 1, we guess is a 2-loop. But when you say 2-loop, is the following. The central charges are built on a surface, out of a surface. But we don't know what this surface is, you see. We haven't understood that yet. We are in the middle of the thing. That's why we haven't published, because there are many, many points to clarify. But it's there. The algebra is defined. The group is defined, the algebra is defined. It's a question now of working out the structure of this algebra. But in 2 plus 1 is very similar to Kac-Mood algebra.
Any further questions? Well, if that's not the case, thanks, Luis.
Thank you. And happy birthday,
Okay, we are finally through closing remarks. So, very quick, 7:30, Cachaçaria Água Doce, Rua 9 de Julho, 1625, 7:30. Don't miss it. Yeah, we meet there at some, what do you suggest? Yeah, please, who knows, lead the mob. So, if we do not arrive before 7:30, we lose the reservation. So, have to be, at least one has to be there 7:30, I'll do that. Okay. But don't let me alone there. For the students in need of support, financial support, talk to me right away. I'm closing here, then we talk. And for organizing this workshop, I had the marvelous help of my co-organizers, Rodrigo Pereira and José Cândido Xavier. I thank them very much. I also had unspeakable help of the secretary, Ms. Ivone. Unfortunately, she could not be here, but I thank her very deeply. And also our technical support, Maicon. Thanks a lot. So give applause for Maicon. He's up there, please. And Saverio probably is around there. And thank you all for coming. And I hope you had a good time. The students, I wish all the best success. And for Chico, you are already highly successful. But okay, you still have some 1 or 2 months, or years, I mean. So more success. And if anyone wants to give a final remark, the microphone is here. Otherwise, no one? Okay. So we meet in the cachaçaria. Okay, Chico wants to give a final word.
Yeah, I thank very much for all the speakers and all the people who attended these lectures and the effort to be here. And I do not deserve 80% of the things the people said, you see. And, but I thank you anyway. And I would like very much to thank Jose, because he did, he said about the organizers, fine, but he did everything. Actually, this meeting only happens because of him. I will not do this meeting as I wouldn't do even the 60, because, you know, I don't know. But anyhow, then he decided I will do anyway, and he did it. So at the end, I thank you very much for doing that. And I hope that I could do your 70 also, or maybe the 60.
Okay, the students, talk to me.